Bluetooth to this. Bluetooth to my ear.
Cool. Isn't technology amazing?
Yeah. They're far back and they're open.
Okay. So now shut it off.
It's down. Good morning, ladies and gentlemen. If I could ask you to please take your seats. Maybe this one is better. Thank you. Welcome to the University of Guelph. My name is Bob Hanner. I'm an associate professor here at the Biodiversity Institute of Ontario, and I'll be chairing the session this morning. Before I introduce our first speaker, I'd like to run through a few housekeeping details. If I could call your attention to the programs, on page 17, there is a diagram showing all of the fire exits in this building, which we are legally obliged to point out to you in case of an emergency. So please take some time to look at the program, familiarize yourself with that and the many different sessions that we have today. I do have a few housekeeping details that I'd like to run through quickly before we get started. For those of you who came in and registered yesterday, we did not yet have our USB keys with all of the abstracts on them. They are now available from the registration desk. So if you registered this morning, you should have received a USB key with all of the abstracts. If you registered yesterday, you might want to stop by the registration desk at some point during one of the breaks to obtain one. I'd also like to ask for all of the presenters to please make sure that you upload your presentations in the speaker ready room. That's 107 Rosansky Hall. For those in parallel sessions, we would ask that you upload your session, your talk at least 4 hours before your session. For those of you who are plenary speakers, if you've not already done so, we'd like to have your presentation at least a day in advance. For those of you who have kindly volunteered to serve as evaluators of the graduate student and postdoc posters and oral presentations, I would also ask that you make your way to the speaker ready room to obtain your score sheets and instructions on which talks and posters we would like you to score. My colleague Sally Adamowicz has sent out emails to you. If you haven't been online, you may not have seen them, but we would ask that you please obtain your score sheets, score those presentations and the sessions to which you've been assigned, and hand them back in at the administration desk in the speaker ready room after each session. Thank you. I do want to point out, we ran a number of tours of bio yesterday. We had dedicated the day for that. Because so many of bio staff are helping to organize this conference, the bio building is closed for the rest of the week and will not be accessible unless through prior arrangement through a personal collaborator. If you were unable to attend a tour, I apologize for that, but please understand an undertaking of this size requires a small army of people, and it's pretty well drained bio. With respect to the post-conference excursions, we had a number of ideas in mind. We only had enough registrants to run the trip to Niagara Falls on Saturday. The other excursions had to be canceled because of a lack of interest. However, if you are interested in attending the trip to Niagara Falls on Saturday, there are still spaces available, but we need to give the tour operator a final count as of 2 p.m. today. So if you're interested in going to Niagara Falls on the post-conference excursion Saturday morning, please let someone at the registration desk know to add your name if you aren't already registered online as part of your conference registration. I would also like to make a couple of announcements about our poster presentations. Last night we had our opening reception in the Science Complex. That is where our poster session will be held tomorrow afternoon. If you didn't already install your poster, we would please ask you to do so at your earliest convenience, certainly by the end of the day today, if possible. For those of you who are travel bursary recipients, we would also like to ask that you please leave your boarding passes at the registration desk. We need to provide these to our funding agencies who provided support for your travel here. There are a few other housekeeping details that I'll quickly run through, in that tonight we're going to do a group photo at 6:15 on Johnston Green. That's between here and Creelman, where you had breakfast. Because of the size of our meeting, the group photo is going to be a bit of a challenge. So weather permitting, we have a drone that will take an overhead aerial photo of us all before we move in to the barbecue. So please do plan to attend the group photo. As long as it's not a torrential downpour, I think it will be quite an interesting opportunity for a photograph of all of our conference participants. I do want to point out that all of our breakfasts and lunches are served at Creelman. If you weren't able to get there this morning, we'll be going back there for lunch, and then again for our barbecue this evening at 6:30 after the group photo. All of the meals and coffee breaks are being provided by Hospitality Services here at the University of Guelph. We're very pleased to be able to bring such fine cuisine for your enjoyment for this conference. And if you have any questions or concerns about logistics of the conference, our local coordinator is Meg Fritchie. Meg, would you please stand up so everyone can see you? She's organized just about every Barcode conference we've had, so many of you who have been to prior conferences will recognize her, but you can direct questions to her and colleagues in the speaker support ready room. And then lastly, just like to say a bit of special thanks to all of the bio staff who volunteered to help make this event possible. You will see our many volunteers in blue shirts around the conference, so if you have any questions about where to find a venue, please see a volunteer. Without further ado, I'd like to introduce our first speaker, Malcolm Campbell, Vice President of Research here at the University of Guelph. Malcolm.
Thank you. Thank you, Bob. Good morning, everyone. On behalf of University of Guelph, I'd like to welcome you here to the 6th International Barcode of Life Conference. We are delighted, indeed thrilled, to be hosting the conference here at University of Guelph, and we hope that you recognize this and have recognized it immediately, that we welcome you very warmly, warmly indeed. Come on, 8:30 crowd, I get it. In all seriousness, we are entirely thrilled to be welcoming you here to the Eyeball Conference. And the reason why we're thrilled to be welcoming you here is because you're conducting research that is truly on the final frontier. The final frontier, many of us are familiar with that statement, that iconic statement. It's been used, of course, by Gene Roddenberry in his iconic Star Trek series. And the final frontier has inspired us as a species to go out and delve into areas of science where we might have not otherwise delved. And in fact, just thinking about this and the final frontier and space being the final frontier, in 1961, Frank Drake derived the Drake equation, a 7-variable equation that described or articulated where we might find intelligent life in the universe. At the beginning of this century, a Canadian astrobiologist, Sarah Seagar, developed the Drake equation a little bit further. She came up with the Seagar equation, which described where we might find habitable planets on the universe. The commonality between those two equations is the fact that they're characterized by speculation. The Drake equation has 7 variables. The Seagar equation has 6 variables. Of those, 6 and 5, respectively, we don't really have a good number. They're truly speculative. All that we can say is that between intelligent life and habitable planets, we can speculate that somewhere there's life in the universe. There's a 0 to 1 probability that off of this planet, one might find life. By contrast, what's a certainty is that there is life on this planet. By some estimates, there's around 8.7 million eukaryotic species that reside on the planet Earth. Of those, we haven't even yet characterized 1 million. It's for that reason, I say, and we here at University of Guelph honor the fact that you are working on truly the final frontier. The final frontier that resides on this planet, that you are characterizing, that you are shedding light on. We honor that notion, the approach that you take here at University of Guelph, because we have effectively one of the founders of that vision right here at University of Guelph in the person of Paul Hebert. Paul, in 2003, as you all well know, articulated the notion of using barcodes to approach that final frontier that we have here on this planet, to characterize the diversity of life that reside here with us, that shape the environments in which we live. On account of Paul's visionary view, in Canada, he was awarded the highest honor that we can award a Canadian citizen. He was appointed to the Order of Canada on July 1st of this year. And please join me in a round of applause for that accolade to Paul. Paul's spectacular vision led to the creation of the Biodiversity Institute of Ontario, which we proudly host here at University of Guelph. It's a very special operation in that it sits outside of department and collegiate structures. It's recognized for its importance in and of itself for fulfilling that role of investigating the final frontier. The fact that we host bio and that we proudly call Paul Hebert, or that we call ourselves Paul Hebert's academic home, and the fact that we host bio and the biodiversity conference here, the Barcode of Life conference here at University of Guelph, I hope stands as testimony to our commitment to the characterization of biodiversity and understanding it and how it fulfills our lives on a daily basis. I'd like to finish with one final point, and I should point out before I finish with that final point that I should have said thank you very much for the opportunity to speak here in front of you today. I am, by training, a biologist, although as an administrator that seems to be receding into the past more and more, like my hairline. And therefore, I'm absolutely delighted to have an opportunity to stand in front of fellow biologists today at what is a spectacular international conference. an international conference that has representatives from Bar Harbor to Beijing and every point in between. It's an absolutely remarkable conference. I'd like to finish with one final point around diversity and the way in which we honor diversity, not just biological diversity, but biological diversity in all its forms here at University of Guelph. I hope that you all noticed that on the Barcode of Life website that there was a statement about honoring diversity and diversity of participation within this conference. I think that that's yet another sign of the way in which Paul Hebert and his colleagues here at University of Guelph honor not only biological diversity, but the diversity of the human species, of the human spirit. And I want to announce today that for all conferences going forward that are supported by the Office of Research at the University of Guelph, that they must similarly have such a strong commitment and a statement to the commitment of diversity within the context of the conference. And accompanying that, a statement regarding harassment such that we promote diversity of opinions, diversity of thoughts, and diversity of participation in all conferences that we host here. And I would like to say that it was really this particular conference, the 6th International Barcode of Life Conference, that inspired my office to take that stance in going forward. So I'd like to thank the conference organizers for their very thoughtful and important move in that regard and moving conferences forward here at University of Guelph. Thank you very much. Final point, I would like to just very quickly, sorry, Bob, I'd like to quickly acknowledge the fact that University of Guelph, of course, would not be able to have this conference here if it were not for the spectacular local organizing committee. I've already mentioned I've already mentioned Paul Hebert. Bob Hanner, you've met this morning as well, and I'm sure that very shortly that you will meet Sarah Damowitz and Mirdad Haji Babai, their co-organizers who've done a spectacular job here at BIO. And now my final point. My final point is that as a fellow conference participant in the past myself, and indeed an organizer of such conferences in the past, and as a person who does a fair amount of long distance running, I'm going to leave you with some words of advice. All conferences, it's important to train for, and it's important to make sure that you are peaking right at the time that the conference starts. And like all long distance runners, you must make sure that off the start of the conference, you do not run overly quickly, but pace yourselves. It's a long conference with wonderful things that are going to happen. And you'll want to make sure that when you get to the finish line on Friday, that you feel fantastic, rejuvenated, and that you've accomplished all that you wanted to accomplish at this particular conference. Again, welcome to the University of Guelph. I look forward to seeing you at some of the conference events this week, certainly this afternoon and on Wednesday evening. Have a wonderful time, and I look forward to seeing you back here at Guelph at some point in time in the future. Again, thank you.
Thank you very much, Malcolm, and thank you to the Office of Research for your generous support of this conference. I'd now like to introduce our next speaker, Dr. Braulio Ferrara de Souza Diaz, Executive Secretary of the Convention on Biological Diversity. Dr. Diaz has over 3 decades of experience in biodiversity science and policy and its implementation at national and international levels. He brings a unique combination of scientific training and extensive experience in negotiation. He obtained his BSc in Biological Sciences from the University of Brasilia and went on to obtain his PhD in Zoology from the University of Edinburgh. His list of accomplishments are long, and for the sake of brevity, I'll leave it there and hand it to you, Dr. Diaz.
Thank you very much, Robert. Good morning to all. Is this on? Yes? It's a great pleasure to be here with all of you, and it's my second visit here to the University of Guelph, and I think it's really, we should be thanking very much the University of Guelph and the Ontario Biodiversity Institute for hosting us here, for organizing such an important meeting. As you know, 23 years ago in Rio, the governments of the world agreed on a number of commitments to face the environmental challenges of the world. Among these, they adopted the Convention on Biological Diversity. And the convention sets to face the challenge of reversing the trends of loss of biodiversity. As you know, we have been facing huge losses for the last few centuries, but especially in the last decades. If we take some examples, like some types of ecosystems like wetlands, we have lost more than 90% of wetlands in the last 3 centuries all over the world. If we take some population of some groups of species that have been overexplored, like large fishes, also it's the same statistics. We have lost more than 90% of the population of large fishes all over the world. And we're losing altogether species, so extinction has accelerated. And unfortunately, we even don't know how many species we have on Earth. We even don't know how much genetic diversity we have altogether in all these species and all these ecosystems. And unfortunately, many people nowadays living in cities don't appreciate how dependent we are on nature for our daily subsistence. So this is a message that we have been trying to push harder in the CBD, that almost everything we do, our economy, our well-being, is totally dependent on biodiversity. We need biodiversity to feed ourselves daily, to breathe clean air, to drink clean water. It's critical to develop new medicines. It's critical for the survival of everyone, especially the poor. If poor people survive in the world, it's because they have access to biodiversity. They can catch a fish, they can catch some roots and fruits, etc. But unfortunately, many people still think that this is not an urgent issue. Fortunately, people now see the urgency of climate change. So that's finally a good trend. So people are finally understanding that this is a critical issue that we need to address. But biodiversity, most people still think that it's not that urgent. We can defer for the future to deal with it. And many people still think, okay, let's first create jobs for everyone, promote the economic growth, etc., and then we'll face the issues related to biodiversity. But they fail to see how dependent we are on biodiversity. So biodiversity needs to come together with any development proposal. So I'm very happy that next month in New York, the UN General Assembly will be adopting the post-2015 development agenda, which is a sustainable development agenda based on the 3 pillars of the economy, the social, and the environment aspects that really provide the basis for all our economy and all our well-being. And I'm very happy that as a key part of this new agenda, the countries will be, the governments will be adopting the so-called Sustainable Development Goals. These are a set of 17 Sustainable Development Goals, including 2 which are fully dedicated to ecosystems and biodiversity, goals 14 and 15 for marine and for terrestrial ecosystems. But perhaps more important, people have recognized the role of biodiversity in other goals. So the goal on food security recognized the importance of genetic diversity. The goal on water, goal 6, recognized that we need to conserve ecosystems, the catchment areas, to protect the water cycle, and so on. So I think finally we're seeing slowly more attention being paid to the biodiversity agenda. We've been trying to push with governments and with the private sector the notion that biodiversity needs to be fully understood as part of the so-called natural capital. So for many countries in the world, their main assets are the biodiversity that they have, and of course, the human resources they have. So these are the two most important, perhaps, assets that any country has, perhaps more important than any minerals or any other asset that maybe people more easily see as economically important. However, we don't know much about these assets. We don't even know how many species we have. We're still discovering a large number of species, especially in the tropics. I'm from Brazil. In my country, the last year, for example, a new species of river dolphin was formally described. Can you imagine a river dolphin that is only recognized now after so many years of research? A new species of tapir, a new species of peccary, more than 15 new species of monkeys, and the list goes on. So we're really still at the beginning of really mapping biodiversity out there. And I think we need to do a much better effort to establish the science infrastructure for biodiversity, because policymakers, managers, they have really a difficult job to do, making decisions every day about something they don't know really what's there, right? So that's why I'm here. I think the work that you're doing here on using DNA to really speed the research on biodiversity, and really developing tools that can facilitate actual decision-making and management on everyday lives. So issues like invasive species, right? It's a growing problem everywhere. With climate change, this will grow even more. Issues of illegal trade of wildlife and timber. Issues of how to detect and monitor rare and threatened species. So there are many issues there that currently it's difficult to handle and to make progress, especially in tropical countries where much of the biodiversity is, because in most places biodiversity is a black box. We really don't know what's there. So we need to invest more on some infrastructure. So just like in other branches of science, like astronomy, so astronomers cannot do much without observatories, right? So they collectively invest in building these big infrastructures for the whole community of astronomers to utilize. And I think the same applies here. So we need to build the libraries of DNA barcoding. We need to build the libraries of information on biodiversity. For example, we hope that finally, after a lot of effort, we'll be able to have at least a consolidated list of described species in the world. We still don't have that for all groups of organisms. All this, we should be treating all this as basic infrastructure to move the biodiversity agenda. So we need more attention from governments, from the private sector, from the academy, not only from science funding agency, but I think we need to explore more the opportunities to benefit from financial support from all users groups. So I think as we succeed in demonstrating more the potential utilization of these techniques and technologies and all the information that is being generated, hopefully we can get a broader range of funding support to really scale up the whole exercise. So I really want to thank very much the International Barcode of Life project, the Consortium of Barcode of Life, the International Development Research Center, and the Japan Biodiversity Fund for helping to make this meeting possible and some of the activities that we're organizing here. I'm very pleased that we were able to fund the training of some experts in developing countries. And we were able, with the help of the group here in Guelph at the University of Guelph, the Biodiversity Center of Ontario, to really train a group of experts from different countries on the techniques, on how you can really utilize these techniques to solve many of these practical problems that they face in other countries. And some of them are here today participating in this conference, so I look forward to meet them and hope that as they return back to their countries, they will really be able to engage their colleagues and provide their governments and their institutions with more information about the real potential of this field of work. As you know, we have agreed in 2010 in Nagoya, Japan, on the current strategic plan for biodiversity for this decade, with 20 specific biodiversity targets known as the Aichi biodiversity targets. Aichi is the name of the prefecture where the city of Nagoya sits. And you have this summary and conclusions of our last report, the Global Biodiversity Outlook Report number 4, which we issued in Korea in our last conference last October. So there are two main messages here. The first is that we really see an effort in every country to really increase their efforts towards the biodiversity agenda in many different ways, including in science, in monitoring, etc. But the main conclusion is that current efforts are not enough. So currently, if we just continue the current efforts, when we reach the end of the decade, I'm sorry to say we will have to agree that we have failed. And that would be a terrible thing to happen. So I've been doing my best to try to engage different communities, different stakeholders, to really encourage them to scale up, to increase their efforts, because I think we have most of the solutions in our hands, such as the tools that you have been developing on barcoding. So there shouldn't be no excuse, oh, we couldn't do these things because we didn't have the information, we didn't have the solutions, the scientific solutions. We have. Certainly, there's a lot of unknowns yet, but what we have is sufficient to really drive a much better policy development in every country, and also to convince the business sector to change their practice, to stop business as usual and really promote a more sustainable practice. I'd like to share with you that we have been working strongly with different sectors to further mainstream the relevance of biodiversity in these other sectors. This year, I had the privilege to participate in the launching of two major science reports on the interlinkages between biodiversity and human health. We had a launch in Brussels in June, together with the World Health Organization. It's a more than 300-page report with 16 chapters showing the different ways human health depends on biodiversity and ecosystems. And last month, I was in New York at the headquarters of the Rockefeller Foundation to launch a very exciting new initiative called Planetary Health. It's a partnership between the Rockefeller Foundation and the Lancet Medical Journal to promote the notion that we need to invest more on prevention of diseases rather than just building more hospitals and more machines for exams. And in doing that, we need to better recognize that maintaining or restoring a healthy healthy ecosystems out there, it's critical to promote our own health. So even simple things like, so research, for example, in hospitals have shown that just by offering the opportunities for patients to have exposure to green spaces, to nature, promotes a faster recovery and a better recovery. So it's a number of these small things that adds up to show just why we need biodiversity. So I hope that with your help, we can really convey the message to policymakers, and both in public and in the private sector, that we can do better, that we have the tools. So one thing I look forward is the results of the discussions coming out in this meeting here, that we can bring back to the CBD. And our next conference will be in Mexico, in Cancun. So I'd like to invite you all, if you can attend there. And the main theme of that conference will be mainstreaming biodiversity in different sectors. So we'll be pushing for mainstreaming in agriculture, forestry, fisheries, tourism, health, and other sectors. So maybe you, in your discussions here, can identify opportunities that with the CBD we can bring to the attention of policymakers, some opportunities for them to agree on at the global level, and then internalize this into their national policies on how to make better use of the progress that science is making, so that they can speed up their efforts and scale up their efforts. And I don't need to tell you, we have a number of issues like invasive alien species, like illegal wildlife and timber trade, like detection and monitoring of rare and threatened species. So there's a whole range of issues where all these methods and techniques and advances and the science that you're making can really help. My understanding is that one of the messages we should be pushing harder is the need to speed up the building of libraries, these DNA barcode libraries, because it's not enough to have the information for a few species, but if you really want to scale up and apply this to as a practical tool to solve many of our issues, we really need standard libraries of DNA barcodes for most of these species, so that this can be really a standard method utilized everywhere. So I wish you all a very successful conference here. I look forward to receive the results of the conference, and please see us in the CBD as your partner. We are here to help bridge the gap, or bridge the opportunities between science and policy making. Thank you very much.
Thank you, Braulio. Thank you for the generous support from the Secretariat and the Japan Biodiversity Fund. Because we're running a little bit behind, Paul Hébert has generously agreed to cut his presentation in half. No, just kidding. A man who needs no introduction, to give our first plenary this morning, my friend and colleague, Professor Paul Hébert.
Thank you. Braulio, thank you very much for all you and your organization are doing to help our science connect with the world. We really appreciate it, and I think you will have understood when you heard our Vice President speak how privileged we feel to work at this university that has supported us over the past 15 years to try and build what I think is a useful model for other places on our planet. And it looks like our graphics have gone to sleep, so I'm now down to a 2-minute presentation. Help. Ooh, that's not a good sign. Well, I mean, what I want to speak to you about, and I think this isn't news to anyone in this room, we are working in, this is like, there we go. Beautiful, thank you. We're working in a science where the subjects of that science are disappearing. There are not many sciences that can say that. Astronomy can't say it. Particle physics can't say it. And Braulio, you raised the point that we don't have an inventory of species on our planet. We certainly don't. But actually, I don't think that's very interesting. That's just the beginning. That's like having a thermometer and saying, okay, we could read temperature. That's not good enough to have a thermometer. You actually need to use it to go out into the real world and measure temperatures and watch how our planetary environment is changing. Similarly, for biodiversity scientists, it's not just the list of species. It's being able to go everywhere on our planet and read those species. And this is going to take a massive scientific enterprise, the like of which our science has not been involved in. So as we look back at the International Barcode of Life project over the last decade, I think it's provided some useful instruction, but it's the beginning point. It's the foundation for a very large program in research that I like to think about that's going to make it possible to address those goals of an inventory of species and being able to track species on our planet in a way that's absolutely remarkable. So I mentioned the fact that this notion of extinction, the loss of the life on the final frontier that we're embedded within, it's recognized everywhere. Pulitzer Prize winning book this year by Elizabeth Kolbert on the sixth extinction. It's been 650,000 centuries since life on our planet was decimated, and we're living in the century where it's happening again. And I don't think history is going to be very kind to biological sciences if we simply sit back and watch it happen. This isn't just the popular press. If you go into the American Museum of Natural History, the Hall of Biodiversity makes it clear that the scientific community recognizes this. If you read a recent issue of Science, you see Mark Urban predicting that 1/6 of all species on our planet could be extinct by the end of this century. That's one species per hour. It's absolutely staggering. There have been calls to actions in various quarters and various justifications. We have a moral obligation to protect life on our planet. The aesthetics of life, that's no problem with biodiversity scientists. We love the organisms around us. But this hasn't led to humanity rushing to put large amounts of money to protect life on our planet. There have been calls and links to planetary sustainability. These are the 9 axes from the Stockholm Resilience Center, the 9 parameters that we really should be probing deeply to protect the sustainability of our planet. Biodiversity is one of them, but many of them are not been looked at in any detail whatsoever. Why press hard on biodiversity when it's one of 9 pieces in a puzzle? I think we need to move away from, if we're thinking about this grand project and the grand challenge that Braulio, you've asked us to consider, we're not going to do it through these very targeted justifications. I think we need to think about the other people that play in big science space. They recognize that we're a curious species. Knowledge is what motivates humanity. We invest billions of dollars as a species every year to understand the world around us. The New Horizons project just flew by Pluto. It cost $700 million to glimpse that planet. I love seeing that image. I think you probably love seeing that image. Stephen Hawking justified it. We explore because we're human and we want to know. Of course we do. It's us. The loss of species is an irrevocable loss of information. Don't let the dodo fool you. Big organisms leave bones, and you can mine those bones, and you can understand that species. But when most of the species on this planet disappear, they leave a smudge of DNA on the forest floor that's gone a day or two later. The loss of information is staggering. The longest book ever written by humanity is Zettelstrom, single volume, 7 million characters. Our genome, the book of humanity, 7 billion characters, 1,000 times longer. the longest book that a human ever wrote. And of course, it's not the biggest genome on the planet. The lungfish, the canopy plant, massive. We love knowledge. We don't burn books. We protect them. The U.S. National Congress Library, $600 million per year to protect information that the citizens of the United States feel is important to humanity. $600 million per year. Right now, all around our planet, this is what's happening. We are burning the books of life without regard, without ever having read them. We need to do something about that. We need to absolutely, as part of a big biodiversity science project, make sure that the books of life are not burned. We need to do this. We need to gather DNA extracts from every species on our planet, perhaps a few representatives, a DNA arc, a library of life, and those extracts are very compact. You can fit 25 million of them in a single shipping container, and we're not going to be able to read those books today. It's too expensive. But we can put those books into archival storage. And some of you may feel this is a bit of a depressing approach. There's life on our planet in a shipping container. But the community we work in, the biodiversity science community, doesn't just grab DNA extracts. We will collect organisms, we will archive those organisms. Each of those DNA extracts will be connected to a specimen whose phenotype we can understand. It's not good enough just to read sequences. We can't reconstruct that organism phenotype. So this is an important part of the work that we can carry out. What are we going to do with all these DNA extracts? I don't like the idea of a shipping container. I like the idea of the model that Norway has created for a very important segment of life on our planet, the global seed vault on Svalbard. We've got agreement to move the most important plants on our planet into storage in this particular facility. Norway's done a good job of it. So I like the idea of them building a second tower on Svalbard, and the global library of life will reside there. And it will reside in other places as well around our planet. But this would be a nice symbolic gesture, so I'm counting on Norway to build that second tower. Now, Braulio has mentioned, and Malcolm mentioned, the fact that we don't understand the number of species on our planet. And how can we fill up that vault on Svalbard if we don't know how many things? The titles of the book, the index, how are we going to do that? And again, as Malcolm mentioned, and you all know, about 1.7 million species on our planet have been named over the last 250 years, and the guess is there may be 8.7 million. So there's a lot of work left to be done. Animal life is thought to be the largest compartment of biological diversity when you're talking at a species level. What would it cost to do the animal kingdom? And we have an estimate of the cost using traditional taxonomic approaches. It's $250 billion to describe 5 million species. And Braulio, you understand big numbers, but I'm pretty sure you also understand that when you talk $250 billion, that just means that science project is canceled. It will never be done, ever. Humanity doesn't spend that much to satisfy its desire to understand. The smart, big science communities understand the top amount of money you can ask for is about $10 billion. Large Hadron, Hubble telescope, that's how much we're invested in them. We need to take that $250 billion and drop it 2 orders of magnitude, $2.5 billion to complete the inventory of life on our planet, and a lot of other things as well. How are we going to get there? George Hale wrote to the Rockefeller Foundation in 1928, just before the Depression set in, and he pointed out these two very important things about scientific progress. The way you move science is with technology and new approaches. And there are times that you can do this, and there are other times that you can't. And in our science, we're perfectly positioned to follow Hale's maxim. We've got new technology. Sequencing technology is moving like a rocket. Sanger, next gen, and next gen we're going to be able to do absolutely incredible things on this front. And then we have this simple little conceptual advance that says you can tell these objects this we're interested in by reading little bits of DNA. We don't need to read entire genomes. It's too expensive to read the genomes. We need to index life with barcodes across the spectrum of, initially, eukaryotes. This kind of project begins to move biodiversity science into mega science, the billion-dollar-plus projects. There have been 22 of them on our planet, and they all follow a fairly formulaic approach. There's a need for a scientific plan with very crystal clear goals that are big, insightful, and that's really, I think, one of the most important things to capture this money. The other thing is we need a management structure. For all projects have a well-defined management structure. They're always international. They are a long duration. People like myself that might be around at the start of them usually, or trying to get them started, usually aren't around to see them actually activated. Hale never saw the telescope on Palomar. He was dead, long gone. So don't worry about a conflict of interest when these old guys like me suggest a project. We're not going to be here to spend the money. You young guys will. Long duration, multi-decadal, and solidarity. And that's something our community finds very hard to do. Get solidly behind an idea and not shoot inwards as opposed to outwards. I don't think we should be shooting outwards either. I just think we should be immensely supportive of our community and the various kinds of science they want to do. But the science that we're doing won't wait. This year, 3 mega science projects were launched. All 3 involve the construction of a large telescope, and they follow this pattern of somewhere between 7 and 10 nations, and the nations rally up and invest somewhere between $100 million and $250 million in these projects. 3 big telescope projects. We haven't been playing in this space. So let's look at one of the big projects and ask what they've done. The Hubble. It's been in operation for 25 years, and this is the publication volume from the Hubble Space Telescope. It rose rather quickly to about 700 publications per year, and it slowly slid up to about 800. That's what happens when you spend $10 billion. This is what happens when you spend much less than $10 billion, and it's barcoders involved. The number of publications has passed the Hubble, and the number of citations actually is about the same as the Hubble papers are acquiring. So we're not completely divorced from, we've not been in mega science, but I would say we're in mesoscience. We're working on a scale that's allowed us to learn some of the ways of collaborating and cooperating that can make it possible to dream big. 2007, we were sitting in this room when we thought about launching the International Barcode of Life project. And we said, hey, in 5 years, if someone would give us $100 million, we will barcode 500,000 species. It took us 3 years to get organized and get the money, enough of the money, to have the courage to say, okay, we're going to go for it. And there's a high risk we may get embarrassed, but we're going to try. And so we launched in late September of 2010. And since then, many of you in this room have contributed to this giant collaborative project. And guess what? These little dots show where barcodes are, and that was 2010. That was 2013. That's 2015. The barcode records have risen, and what about that target of 500,000 species? Guess what? We passed it last week. We're over 500,000. 500,418, I think it was when I looked. And honestly, I didn't quite believe it, so I yelled at Sajeevan and said, don't tell me you're fudging the results on bold. He promises me, he didn't. Okay, so we've made that eyeball. You in this room have made it possible for us to reach this target. But we've only begun. It's 5%, 10% of the species on our planet. What have we learned? We've learned that we can collect organisms. We can collect them in various places around the world. We found that some of the earlier objections is we're not going to be able to get the specimens to analyze. We satisfied that problem in spades. We could have had tens of millions of specimens if we'd had the resources to run them. We'd never done a big sequencing facility in our community. 5,000, 10,000 specimens per year was sort of thought to be rather good. The little facility that many of you have seen, that small building over there at Bio, ran 1 million specimens through the analytical chain last year. 1 million in a single year. That's been my grand goal for a few years, to see if we could hit 1 million. It required working 6 days a week and some really fantastic people who worked there, but we did it. So we can run millions of specimens. We needed an informatics platform, and that has been assembled with the help and advice of people around the world. So we have somewhere to store the data, we know how to collect the specimens, we know how to sequence them. What we don't know, can we barcode the planet? Can we build this comprehensive reference library, Braulio? And one of the problems is we don't know how big the job is. It's 10 million, it's 20 million. But what we have been doing over the last few years is working in Canada to ask, can we barcode all species in Canada? Now, you've seen Guelph. Canada's a big country. It covers 7% of our planet's land surface. So it allows you to get a little bit of a sense of how difficult it would be to sample in different places. Biodiversity, we're not Brazil. We're 1% of the world, but in many studies that have been looked at in different groups of organisms, Canada hosts about 1% of the species on the planet. So if you could do it in Canada and then you can do it 100 times around the world, you've done the world. So, what do we know about Canada? We know that there are about 120,000 species in our nation when the work began, about 10,000 species of plants, 85,000 animals. And these are the groups that we focused on because their taxonomy is best. We wanted to ask, can we finish them? The plants, vascular plants are done. And one of the reasons vascular plants are done is because herbarium sheets were just an excellent source of DNA, and we could rapidly drive through the plants. So I see no problem doing the plants of the world. There's only 400,000 plus species. Non-vasculars we will have done by 2018. So when you walk out into nature in Canada by 2018, plants are going to be under control. Animals, we encountered a few more barriers. One of them is there are many undescribed species in our country. Our taxonomic capacity is declining. So we had real problems identifying specimens, despite some help from friends. And the other problem is sequence recovery. The animal specimens, a lot of them were old or they were informal. And so really we had to think about launching a new collection program. And to solve this thing, we had to figure out how we could process lots of things where taxonomy was not in place. The taxonomic problem was solved in the animal kingdom by moving towards a DNA-based system, looking at sequence clusters. And here you can see some standard sort of barcode sequence clusters, and connecting this with the bin system, where all of those clusters are assigned a persistent identifier, and now bold as each sequence enters bold. It's an animal sequence. If it meets the quality standards, it gets assigned to a bin. And there are, as of later next week, 400, and now it's about 419,000 pages like this that assemble specimen information, distributional information, images of each of these species, the 420,000. And I say species, even though they're sequence clusters, because there's a wonderful mapping of bins onto species. So here's Canada, a bunch of groups. Rosemary, you won't like to see this, or maybe you will like to see the fact that the spiders, those are the spiders that are sitting up there above the line. I don't like them. The others are sitting on the line rather nicely, but we actually think there are quite a few cryptic species of spiders not recognized by current taxonomy. What happens in Canada happens in other places in the world. There's a very tight correspondence between species counts and bin counts. It's the automation of this one really important axis of biodiversity measurement. We can now automate the counting of animal species anywhere on our planet simply by gathering a little CO1 sequence and slamming it into the Russell algorithm that assigns and creates bins. So we now can count, and this has been invaluable for our work in Canada. But the automation is not yet complete. There are other things that we can do, and one of them is we can ask how many species, what fraction of the species are shared between sites. Just press a button, and you can see that 1% of the species are shared between Costa Rica and Ontario. You can see that 18% of the species are shared between Costa Rica and northern Argentina. The automation of biodiversity science, this is where we must head. The other thing is it's not complete yet. There's a lot of phylogenetic signal in the CO1 sequences, and I don't have time to look at this in much detail, but here you can look at two rather closely allied insect families. These are circularized neighbor joining trees. Green are ichneumonids, red are braconids. You get this perfect separation of these two insect families based simply on CO1 sequence information. And that's true for family after family. The taxonomic community has built a wonderful skeleton of biological diversity on our planet, and now we can use that to place unknown taxa. So this is where we're headed. You go out into nature, you collect a specimen, you sequence that one little gene region, and you can place it to a phylum. You can place it to a class. You can place it to an order. You can place it to a family. And in some cases where taxonomy is complete, you'll place it to a species, a Linnaean species, but in lots of others, the terminal point will be a bin. The automation of this critical aspect of biodiversity science made it possible for us to go out and look at biodiversity in Canada in an extensive way. What about recollecting species? I said that was a problem. We have 30,000 species of insects known in Canada, just 30,000. It's thought there may be 55,000 species. So that was our target. How tough is it to go out and recollect 30,000 species of insects? Going to take you forever? We decided it was important to get school kids involved in this, so we sent out a malaise trap earlier this year to 68 schools across Canada at those sites and said, kids, collect bugs for 3 weeks, send them to us, and we're going to barcode about 15,000 of them for you. And when we did that, we found the school kids had collected nearly 3,000 bins. They collected 10% of the insects in 3 weeks. And guess what? They were grade 5 kids. So I don't believe anywhere on the planet we can't do this kind of sampling and get a good indication of species. And then you don't need to look at a whole bunch of places. You can come to my backyard, as we did, set up a single malaise trap in my backyard for a couple of years and ran just a fraction of the specimens. And I share my backyard with 4,700 insect species. 16% of our known fauna. And we went to our national parks and we set up a malaise trap in each of the 45 national parks just for one summer, and then ran about 800,000 specimens, 20,000 per park. And we did that. There's the known species. There's the bin count from this little national park survey. We collected 133% more species than are known from our country. And when you put all this together, the various sampling sites, 29,000 species known, we've now collected nearly twice that number from sites in Canada that we have sampled over basically just a 3-year period. We can rapidly make fresh collections and inventory life on this planet. On animal species, we're up now, not just insects, of course, we've been analyzing, we're up at about 40% more than the number of known species. So I take these results as very good indication that we can actually get a lot done relatively quickly. And Bob, I'm really conscious of the time. Shall I just jump right through these things and not talk about them? Are you sure? All right, otherwise all right, so I'm going to try and rush through these things. But we're working in Canada and we're trying to find out, and the question you want to ask yourself, of course, is does this help inform something larger? Does it help to tell us about how accurate the counts are of animal species on our planet? The forces limiting diversity. How old are species? There's a nice paper in PNAS just earlier this year by Nigel Stork and colleagues that said, look, if you want to understand animal species on the planet, you need to count beetles, because beetles are almost all animal species and almost all animal species are insects. So just count beetles. And the estimate they came up with 1.5 million beetle species, and there are 5.5 million insect species on our planet. This is sort of an important question to answer. How accurate is it? They're pretty sure it's quite accurate. But we've been doing this in Canada, and Canada has 1% of the animal species. Here's the log of the known species, and these are the log of the bins. And you can see that almost, these are 30 insect orders. 28 insect orders. Most of them fall under the line. We only collected at a few places. We did not collect all of the species known from Canada. No surprise. This is a log scale you may note here. Diptera and Hymenoptera fell way above the line of known species in Canada. And in fact, if you do a log normal prediction, 7,000 species of flies known in Canada, we've got 36,000 projected now. A gross, far, far, far more fly species in Canada than beetles, that's for certain. And far, far more than we had anticipated. Those flies, did you find crazy diversity in all fly families? That sort of interests me. Dan hates this kind of science. I just love it, but Dan just hates me for wanting to count species, and I'm always trying to convince him it's worthwhile. I probably will fail again in the morning. There's the regression between number of known species and the number of bins observed. A nice tight correlation with two exceptions. The sesiomyids and sciurids have gone crazy. Isn't it interesting? They've got an unusual breeding system. They're haplodiploid. And in fact, when we sit back and look at sesiomyids, we've already observed 8,000. We've run 90,000 specimens, and the number of bins based on a log norm model is 15,400 at the handful of sites, the 45 or 50 sites that we've sampled. That many species. Based on the insect work that we've done in Canada, we're now estimating there are 95,000 species of insects in Canada. There were 25,000 known, and prior work had estimated there might be 55,000. And so we've just about doubled the known species count of insects in Canada. And if you place this in a global context, back to the old 1% rule, there are 9.4 million species on our planet, not the 5.5 million that Nigel Stork had estimated. Sesiomyids, we're now estimating 20,000 species of sesiomyids. Prior work was of 1,000 species in our nation. And you put that in a global context, 20,000 species in Canada, 2 million species of sesiomyids. What are the implications? Well, the one thing we've got to do is go back and tell Haldane he was wrong. God does not have an inordinate fondness for beetles. He does for stars. They're 10 to the 23rd stars. But beetles, nope. On further thought, stars and midges. And in fact, I'm not prepared to jump quite that far yet because, as Mark Blackster will certainly remind me, we don't have any clue how many species of harpacticoid copepods we have on our planet. We don't have any idea how many nematodes there are. Mites, it may well be that these are the really hyper-diverse groups on our planet. So we can't estimate species. These efforts to estimate species without data, you need to come out and look at these hyper-diverse lineages before you come up with species counts for our planet. What is the implications of this? I mentioned earlier, of course, the people have been down this road before, and one of the people who have been down this road is the astronomy community. Naming conventions. We used to name stars until Mount Palomar opened up the heavens, and what did astronomers do? There are too many stars to name. So they moved away from naming things to moving them into a coordinate system. And I'm certain that as we begin to reveal these immense pools of biological diversity, unnamed biological diversity, we need to think about a new naming model. The fact that we're probably going to be, this is going to be the terminal state. No one's going to pay to name 2 million species of sesiomyids if that number proves accurate. But this is very functional. What limits the number of species? There have been two competing hypotheses. One is competition, and the other is it's damn difficult to speciate, and so you're going to have, there'd be a species under every bush if it was easy. And I'm thinking that when we see these explosions of diversity in haplodiploid organisms, that this is telling us something about the factors that regulate species numbers, animal diversity on our planet. Dan, it is important to do this work. Species ages. We love understanding speciation. The cichlid fishes of Africa, these model systems of very young groups are very attractive as we probe evolutionary patterns. But our science, evolution, is based on case studies. whoa, what the hell is that? Oh, that's a regression line with an R squared of 0. The one, we're now working on continental scales, not with a single group of fish or the single beetle genus. We're working on every genus, every species on the continent, and guess what? There's the mean nearest neighbor distance. There's the number of congeneric species. The cichlid fishes are out here. 0 divergence. And in North American Lepidoptera, 1,100 genera looked at. Those are the cichlids. Those are the things with no divergence. The species that we share our planet with are extremely old. 6.27% average nearest neighbor distance, about 3 million years old on average. So, are estimates of global number of species accurate? No. We're overlooking diversity in these groups that no one has studied. Has competition been the primary force in limiting number of animal species? I think we need to give thought to the fact that genetic factors may be playing a really prominent role. Are most animal species old? Yes, they're worth saving. Can we barcode the world? I think so. In Canada, we've done these groups. We've got work left to be done. It took us 1.5 million sequences to do this. I think we can finish Canada for another 1.5 million. If Canada's 1.1% of the world's biodiversity, this is what we need to do. These are the sequence targets. How will we get there? We need to create a massive mega science project, a planetary biodiversity mission, which is going to probe species with DNA barcodes, but that's only the beginning. That helps us get to the inventory. An inventory of species coupled with ecology, evolution, and morphology of these organisms, a library of life up to Svalbard, all of those DNA extracts stored for future genomic analysis, a big effort on advanced biosurveillance that allows us to read biodiversity anywhere on the planet with ease. What do we do now? 2016 to 20, we clarify scientific goals, build support, secure the funding, a 20-year project, and we can complete this. Probably you will have it by 2040 if you get us the $2.5 billion. This room, archival nodes we need to collect around the planet. These are the nations that are represented in this room today. There's no better recruitment center for the collection program that needs to be associated with this project. We need to sequence them. I think we need to think about creating biotrons, big analytical facilities that are all analyzing about 1 million specimens per year. You do this for 20 years and you've analyzed the 300 million specimens. We've got an informatics platform. No problem to expand it. I think this is an important, really important thing for us to think about. The people in this room are taxonomy, and we've tried to spread things out. Past barcode meetings have been pretty much the biodiversity science community, but we felt it's really important to this meeting to bring in the disciplines. If we're going to launch this project, we have to have the smartest thinkers in ecology, evolution, people who understand the technologies, and people understanding genomics. This can't be just a biodiversity science project. It must be very broadly based. We need linkages with the key organizations around our planet that help and focus on biodiversity issues. So, my final slide, you'll be happy to know. We live at a time when life on our planet is threatened. We live at a time when technology is making it possible for us to read life on our planet. We've shown that we can work together as a community. Canada's been a useful pilot project, and this is what we need to do over the next 20 years to get us much closer to protecting the species that we share, are embedded with in this final frontier. The work I've talked about is only due to the fact that there are 243 magnificent people that have worked at bio. This Wordle, the size, number of years they've worked at bio, it's way too cold. I don't like it. I mean, these people are very passionate about what they're doing, and so I would like to see some hotter image, but I can't figure a way to present them. I deeply appreciate their commitment to our work. And of course, the work would have been impossible without funders in Canada and colleagues around the world that have made this possible. So thank you very much, and my apologies for going a bit long.
In the interest of being respectful of our other speakers, you'll have to find Paul at the coffee break or later on during the conference and corner him to ask your questions. Thank you for setting us on a mission, the Planetary Biodiversity Mission. I'd now like to welcome Dr. Yves Bassett from the Smithsonian Tropical Research Institute.
Does that work? Is it working?
Yeah.
Yeah. Okay.
That's like that.
Okay, great. Cheers, thank you. Okay, Control L. Maybe just to...
I just need to put it on the other screen. Just one.
Okay. Well, good morning, everybody. After this magistral opening by Paul, I'm going to have a fairly simple presentation here. It's going to be not so much about DNA barcode per se, but really about the use of DNA barcodes in specific research program. Like here, I'm interested in long-term monitoring of arthropods in tropical rainforest. We have a program called the CTFS Forest Geo Arthropod Initiative. This initiative depends on the Smithsonian Institution. And then we are working here in a network of forest permanent plot, the Forest Geo network, mostly situated in tropical rainforest. That's currently 61 sites representing 24 countries. Every 5 years, those trees are surveyed and measured, so that about 6 million of trees are being monitored, representing 10,000 species. Within this network, we have 10 science initiatives, including this arthropod monitoring, where we currently work at 9 sites. Those are the sites which are included here in the map in yellow. And I'm going just to talk about the Panama site, because we started in Panama, and then we have longer consequences for Panama. So the aim of this initiative is to monitor key insect assemblage over the long term inside this network, and as far as possible to study insect-plant interaction also inside the network. And to do that, we focus on a priority set of assemblage, of insect assemblage, which were chosen for the ecological relevance, also taxonomic tractability, and ease of sampling. That's very important. So those assemblage are simply litter ants, also selected moth and butterfly, which are important herbivores or pollinators in forest. Bees, also important pollinators. Termites, which is important decomposer in the forest. Tephritic fruit flies, which are seed predators, and the whole guild of seed predators also, which are extremely important for the regeneration of the forest. In Panama, we actually study a full suite of 15 taxa. The methods that we're using to study those groups are pretty straightforward. They're very simple. We're using Winkler extraction for the litter ants. Also, we attract bees or tephritic fruit flies by chemical baits. We attract moth and other taxa by light, and then we also search for termites in different quadrats, and also net butterflies in walking transect. So everything very simple. In terms of interaction study, we are mostly interested in insect seed predation and trying to develop local quantitative food webs. Actually, we're working in Panama, in Papua New Guinea, and in Thailand doing this. In terms of taxonomy, well, we have local reference collection, which are often managed by field assistant, by parataxonomists, if you want. We are, of course, trying to do as much as possible DNA barcoding, so more about this in a moment. We collaborate with experts, but of course, there is a fairly high taxonomic impediment, as you know, in the tropics. So an example here from Barrow, Colorado Island. We started in 2008, so we are now in the 7th year of this monitoring business there. And then just to give you an idea, we have about 36,000 specimens in our collection, which are focused on 1,800 focal species. Out of those species, we got about 17% which have actually barcode index number. The main use of DNA barcoding in the context of this research program is, of course, to refine the delineation of the insect morphospecies, and as far as possible to identify the common and the abundant species, because they are the only ones which are likely to be tractable in long term. And currently, we have accumulated 10,000 sequences, mostly from Panama. And I must point out here that some of the area where we work have already extensive barcode library, like Papua New Guinea has 25,000 barcode for Lepidoptera, but others not, like in Thailand. So, of course, our approach for barcoding needs to be different for each site. The interest of DNA barcoding, as I say, again, it's a refinement of reference collection that's very important for us. And then, for example, I can argue that in Panama, no, thanks to this monitoring business, we have probably the best actinic on geometry moth collection there. Of course, the baseline on ecological survey is very important, and Dan is going to talk, I'm sure, about Guanacaste in this regard. What I just want to point out here is that when the monitoring protocol are actually reasonably similar to the best collecting methods in the field, then you could have reasonably good species accumulation curve, reasonably good representative tree, and document well the fauna. That's the example here of the Saturnine moth that we collected at Light in Panama. The other interest of DNA barcoding is, of course, to allow matching the sexes in case of sexual dimorphism. That's very important for us. Identification of early instar, like caterpillar, pupae, rear parasitosis. I'm sure we'll hear lots of talk about this during the conference. But also to match the cases of social insects, such as here, termites. We collect alates of termites in light trap. But the taxonomy is actually based on termites mostly on soldier that we collect in termite transect, so we could use the bin just to match those different cars. But also I want to point out that barcoding allows the monitoring of functional groups, which are important for the forest ecosystem, but not well known taxonomically. And that's the case, for example, of Flatidate, those are sap-sucking bug which can transmit viruses, so they're very important in the forest regeneration. But currently we know very little about them. On looking at bold sequences, 10% of all those bold sequences from Platid are coming actually from Barrow, Colorado Island. So I just want very quickly, just to provide you some selected, example of results here, and I'm going just to talk about yearly results, so annual indices that we can derive for each of those different assemblage, those different species, the population dynamics, but also the yearly changes in the assemblage. For each of those results, I'm going just to emphasize the immediate significance of the result versus the, the interpretation of the long consequences, because we don't have them yet. So an example, again, all examples are coming from Panama. So from year 2011, we have derived annual indices for butterflies here and then for ants for different species. And then we collected that here about 17,000 specimens. And for 56 species, we could really derive fairly good, indices of abundances during that year. That's not a very high or large proportion of the species that we collected in terms of diversity, but in terms of abundance, that represent more than half of the total abundance of the focal species, so that's fairly representative. And I just want quickly to point out that we need to derive different indices for the non-social insect, like butterfly, and then for the social insect, because there are some bias due to the proximity of the nest of social insect when you sampling in different sample. That's one of the points that I've here just to summarize what is the sort of immediate significance of those data. I would also say that the common species can be monitored with relative precision, even in tropical rainforests, and that's very good news because we have very few long-term monitoring programs in tropic, and they invariably concern fruit-feeding butterflies. And also in Panama, basically all our common species for which we can derive annual indices, they also are barcode index numbers, so they're fairly well characterized. So another example here about the population dynamics. Those are Saturnine moths collected at light during the last 6 years. And those are different plots for different species with, if you can see that in gray, the raw data, and in black continuous line, the very simple model, a time series model, which is testing, or different set of model testing, whether, for example, here, you have no effect of time, or here you have a linear increase with time of the abundance of the species, or an effect for each time point here, like in this case of the species. Similarly, those are data for butterfly of Panama, again, of Barra Colorado Island, the last 6 years. And in here, we split the data set according to the gilt, to the way that the butterfly feeding, either exclusive feeders on herbs, which are actually plotted here in gray again in the top part of the figure. And that's here we could fit a model for each time point, which indicate that there is a moderate increase if we compare 2014 to 2009, the baseline data. If we fit the model to butterfly feeding on trees, which are in the blue line, or on liana in the orange line, we cannot fit the model, so possibly something is happening here between those different categories of butterfly. So that's the point here, is that the population dynamic might depend on the ecology of the species. We can also detect significant changes in the species. Of course, this is in the short term. On nearly a quarter of the species show some differences. But what is important is that it's, for sure, the species identity is crucial, so therefore the barcode index number are really essential in this monitoring business. Briefly also about yearly changes in assemblage. Those are ordination of the different species by different taxa across the year. And then looking at butterflies here, looking at geometrid moth, bees, flattidae, so sap-sucking bugs, ants and termites, collected with different protocol. And then here, in the ordination, I joined the different years, so we can sort of visually assess the trajectory that those different taxa are taking. And it looks like they are mostly independent. Furthermore, if we look at here the same monitoring protocol, like light trap can collect different taxa, like again, geometrid moth, another type of moth here, actin, assassin bugs, those are Reduvidae, predatory, again, the Flattidae, Passalidae, which are wood-boring beetle, annelids of termites. Again, those trajectory are mostly different from for those different taxa. A similar setting here with comparing on top of the figure the Reduvidae, which are species-poor assemblage, with the crambid moth, which has a species-rich assemblage. And here looking at either all the species together, to compose those matrices for the analysis, or only very common species, or only species which have barcode index number, which basically are mostly common species and a few other. Here, those are very good news because we see that, especially for the species-rich assemblage, that there is basically no differences. Here, the trajectory are similar, which means that instead of considering all the species for those analyses in the yearly changes in the community, maybe we could use only the common species with barcode index number. And that's one of the points of summarizing the immediate significance of those data. But the other one, which is important, is that those trajectories are really independent for the different taxa. So there is a need to monitor an array of taxa. You cannot just go in the forest and start monitoring fruit-feeding butterflies, for example. You will need to monitor all those different taxa to have an idea of what they're doing. Like all of you, we have a challenge here. It's publish or perish. And then, of course, this challenge is rather acute for us because we need to wait for the quality data to accumulate so that we can run analysis on long chronosequences. So I think there are different remedies in our case. One is just to compare the insect data with other sites. It's widely underappreciated that tropical insects are not very well sampled and not with the same protocol. So that's very important to run those comparisons at different sites. We talk about faunistical survey. We can also mine barcoding data and also publish data release paper. But if those data are available, we can also mine historical data. And then in just a few minutes, this is the example I would like to talk about. It's looking at the extension of the butterflies of Barrow Colorado Island since the 1930s. We compiled records of butterfly for BCI, for Barrow Colorado Island, during the period 1923 to 2013, basically to nowadays. And then we recorded 600 species during this period. And then we comparing to an old and a recent period, 1923, 1943 as the old period, 1993 to basically nowadays for the recent period. The old period is basically based on several compilations, but including the very good list of Huntington, who was published in 1932, whereas the recent period basically referred to all the monitoring. So just a quick sort of history of the island. So in the 19th century, what was then the island was composed of 45% of old growth forest. The rest was shifting agriculture. And then circa 1910, this island become 1,500 hectare island after the Chagres River was dammed to create the Panama Canal. And in the, in the whole period, the period of interest, it was already 97% forested. The rest was clearing on small agricultural area. Today, we can consider it to be 100% forested. So the main changes here was succession, reforestation of the island with the fragmentation and disparition of herbs and crops. And so in this list of 600 species, we actualize the list and then we mine the bulb for barcode index number. Of course, many barcode index number came from our own data from Barrow Colorado Island, but we mine also in gray those barcode index number from other projects, and there is a certain number of species for which we do not have the barcode index number. That's the distribution of those different categories of barcode index number for the subfamilies of butterflies. And since we're doing an old versus a recent comparison, it's legitimate to ask whether it's really good to make this comparison in terms of taxonomic knowledge. So of course, if we plot the description of the year of description of the species, it's all started with Linnaeus, and then we have Bates and Goldman and Savin. This is the Biology Centralia Americana, which actually made tremendous gain in terms of the historical knowledge. But you can see here that at the time where Huntington published his list, we had already a fairly good taxonomic coverage of those species. And of course, there is a certain number of species who were then described after the date. And then, of course, we have now the sort of the cryptic species, the species which were discovered by the new molecular methods. But it's basically legitimate to do this comparison. So what it boils down to is first, we need to notice that the sampling effort during the recent period was much higher than during the old period. Still, beside this, we had 23 abundant species during the old period could not be recovered during the recent period. So we consider that those species are locally extinct from the island. And of course, we cannot discount that there is misidentification of those species, but the comparison of the barcode index number is sort of reduced this possibility. It's not totally clear, but it does help a lot. In terms of looking at the phylogeny here, we also use the barcode, the DNA barcodes, just to make a pretty simple phylogenetic trees, just to also which here the barcodes are concerned to match the interfamilial relationship. And then we plotted on this simple tree the extinct species, and this is in orange or in red here. And then you see that they do not cluster very well into the wall of the tree for all the butterfly of the island, so that the phylogenetic signal of extinction is weak here. We also look at the potential predictors of the probability of extinction for those species, and this independently of phylogenetic relation, because we could infer that from the bin. And we, excuse me, we actually saw that one of the good predictors of the probability of extinction was the host growth form. So whether the butterfly was feeding on liana, on herbs, on tree and shrub. And then here, those are different categories of abundance of butterflies. And then we comparing the common extant species with the extinct species. And here, the proportion of species who were extinct but feeding on herbs is actually higher than for the common species. Another predictor is wing size, so the size of the butterfly, with on average having more a proportion of higher species of extinct species being very small. That indicate food dispersers. So in conclusion here, we could say that those 23 species who are considered to be extinct, that's only represent 6% of the recent records. And that the most likely candidates for extinction were small hesperids, those are skippers, feeding on herbs. And those small species probably poor disperser, and then they might find difficult to find the herbs who have sort of become fragmented and more rare following the reforestation of the island. But I think what is also important to realize is that during the same period, the isolation of the island from the mainland, we lost many more bird species, vertebrate species. We lost about 50 to 60 bird species during this same period. So that's an indication, again, that small reserve, like here we have only 1,500 hectares preserved, are still effective for invertebrate conservation. On just as a final point, the future of monitoring, of course, for monitoring program like this, it's clearly meta-barcoding with a fine example of the global malaise program, and I'm sure we're going to hear a lot in this conference about this fine program. Of course, for us, what is interesting, the presence-absence data are interesting in terms of monitoring, especially if you have spatial replication. But the abundance data might be a bit more interesting. So we're really thrilled to be also helping this program. We have a malaise trap in Panama and also one in Papua New Guinea, and I hope we will have one in Thailand next year. And I think it's the opportunity to calibrate and test those methods, especially in species-rich tropical, habitat like where we're working, where we also are trying to accumulate barcode index number for those different species. So very briefly, the conclusion here, we have an nascent mini network focused on monitoring arthropods in tropical rainforest with adequate protocol on including DNA barcoding. Common species of tropical insect can be precisely monitored in the long term. And I think this is important because most insects have short generation time in the tropic. It might be possible to develop efficient warning system that can yield result within 5 to 10 years. This basically is equivalent to 40 to 80 insect generation. So that's rather substantial. And I will just finish here just by an invitation to collaborate with us. We have, to the analysis on monitoring on barcoding data, we basically collectively, we have accumulated data on 0.6 million specimens. We have 6,000 species and 10,000 sequences. And I briefly just want to acknowledge all the institution who helped this program, the many colleagues also well, the organizer for inviting me, and you for listening. Thank you.
We can take one question as we're preparing to shift over. If anyone's got a burning question for Yves. Here, use this.
I was struck by the divergence in your estimate of the underestimation of species description and Paul's enthusiastic overestimate of how many species we haven't described yet. You were suggesting that maybe there's a 10% or a 15%.
Or in terms
deficit?
of cryptic species. Well, I think we didn't have enough, we're not the beneficiary of so much funding then, of course, but I think, yeah, it's only 10%, and I think with Dan, it's what you have, 20% of cryptic species or 15% or? I'm asking about the proportion of cryptic species, basically in the total, like if it's 15 or 20% in Guanacaste. Cryptic, like basically only not formally recognized, and then just with the barcode index number. Well, I think that's it's much more than but I think it's probably much more anyway that those 10% because we don't have a lot of funding to run to all those sequences.
Mark, maybe we can pick up this question at the coffee break. I'd like to welcome our last speaker before the break, Tetsukazu Yahara from Kyushu University in Japan. Perhaps while we're switching over, if there's one more question someone has for Yves, we could entertain it while we're doing the presentation. All right.
Okay. Thank you very much for inviting me to this wonderful conference. Over the last 4 years, I have been working on tropical Asian plant diversity. And our project is sponsored by the Ministry of Environment, Japan. And the goal is to assess how rapidly plant diversity is being lost under the rapid loss of tropical forest in Southeast Asia. As you can see in these maps, tropical forest coverage is unfortunately reduced to less than 50% in Indochina, in Sumatra, and in Borneo, particularly in lowlands. Unfortunately, we cannot see good forests in most areas of Sumatra and Borneo now. Only in national parks or in some reserves, we can see a tropical forest. It's a sad fact. And maybe many plant species are being lost. So how serious it is, that is our question. And so I'm going to talk about 3 topics: trends, status, and extinction risks. To assess trends of species, we need to have a very good time series data, but it's not so easy to get good time series data in tropical Asia. Unfortunately, in Cambodia, the Cambodian governments established some good forest plots, and we are working there. And we could demonstrate how tropical forest in Cambodia is changing. So at first, I'm going to talk about these findings in Cambodia. And secondly, I would like to introduce our Asian-wide survey on all the plant species, or vascular plant species, because in forest plots, in most forest plots, only tall trees are recorded. But under the rapid loss of forest, not only trees, but also shrubs and herbs and vines and epiphytes are being lost. So we need to assess all the species, but it's a big challenge. So we are using a smaller plot, 100 meter times 5 meter. But we placed them in Vietnam, Cambodia, Thailand, Malaysia, and Indonesia in many locations. And by using this state data, now we are trying to assess extinction risks without time series data. It's a challenge. First, let's start from Cambodia. In 2010, I first visited Cambodia, and I could see a very good forest in Kampong province. But in the next year, this forest is gone. Even though this is a governmental forest and there was a forest plot here. So in the next year, we couldn't see anything in the forest plot. And so the Cambodian government placed several, many forest plots in several locations. And I'm going to talk about 32 plots in Kampong Thom province. And before my work, Top et al. Published a survey of forest community structure. In that paper, there is a list of species like this. But you can see that many species are unknown for scientific name. Only local name is listed. 80 species, 36% of 243 total remain unidentified. And I soon learned that identified species, those are also very often misidentified. So finally, I decided to collect again all the trees of governmental forest plots and identify them. And to identify those species, finally, we identified 347, and we sequenced all the species for RBCR and MATK. And those sequences are quite helpful to identify species. This is a case of one unknown species. This tree has alternate simple leaves without any serration teeth, and no stipule, no sap. This is a very common morphology of tropical trees, and it's very difficult to identify this. But by using the sequence, we could know that this is a member of Ixonanthaceae. This is the first time for me to know about Ixonanthaceae. Maybe most of you don't know about this family, small family restricted to tropical area. And later, we could collect a flowering specimen of this species, and by using the authentic specimen image, we could determine that this is a collection of Ixonanthus reticulata. And finally, so we published a taxonomic paper for a Cambodian plot in Kampong Thom. And also, for all the species, we made a PowerPoint slide like this, and also all the specimens are scanned. So by using those images, we published a picture guide for forest trees in Kampong Thom and also Kampong Chnam. And we are preparing several other volumes. And you can download these from our website. And this is quite useful for identifying Cambodian trees. And by using those identification, we could determine how species richness and also phylogenetic diversity and the phylogenetic community structures are changing. And this is an example of a 50 meter times 50 meter plot, KT05. You can see that between 2004 to 2010, many trees indicated by red crosses logged and gone like this. Those loggings are, of course, illegal. And so between these 2 years, species richness decreased in many plots, and also phylogenetic diversity decreased. In those plots, species richness is highly correlated with phylogenetic diversity. So you can see two figures are almost identical. And this axis indicates difference between two successive surveys for phylogenetic diversity. And if so, illegal logging is made on more trees, then PD loss is more serious. But if new recruitments, there are more new recruitments, then species phylogenetic diversity slightly increases. So undoubtedly, illegal logging is serious effect on phylogenetic diversity loss. And these figures shows changes of rank abundance relationship. Vertical axis is abundance of each species. And you can see that dominant species, abundance of dominant species reduced from 2004 to 2010. And in particular, Syzygium chanlos is almost low, and this Diospyros venosa is increasing. And under these changes, phylogenetic community structure is also changed. In 1998 and also 24, we can see three very distinct forest communities. One is a dry dipterocarp forest, and two different types of evergreen forest. However, in 2010, these three types are disappeared, almost disappeared, because under illegal logging, some evergreen plots became similar to dry dipterocarp plots under the invasion of some pioneering species, gap species. Those are mostly deciduous. So this is a very good example of demonstration of community changes based on DNA sequence and phylogenetic community measures. Let's move to status survey in many Asian countries. Let's start from West Kalimantan. Kalimantan is an Indonesian side of Borneo. There are several nature reserves and national parks. Mandol Nature Reserve is one of them. Except for those reserves and parks, we cannot see any forest. And in Mandol Reserve in 1987, Dr. A.G. Suzuki, worked on so established a forest plot and worked in vegetation of this area. And in that time, he used sheep to move, transverse this Mandol Nature Reserve. However, in 2012, I visited here, and I could move by motorcycles. This is my picture. This is because sand gold mining is going on in the core area of nature reserve here. It's too bad. And Here we worked on changes of tall trees in 1 hectare plot, and also we started to use belt transect of 100 meter time 5 meter. And 100 meter is divided to 10 sections of 10 meter. And we recorded all the vascular plant species within 5 times 10 subplot. Those include herbs and shrubs and vines and epiphytes, everything. As for epiphytes, we are using a tall pole with a knife on the top, and the height of pole is about 15 meters. This is an example of transect record. So we started here, and number 1 is Dipterocarpaceae, Shorea stenoptera. And we recorded 334 species. The last one is Goniostyrus of Timeriaceae. And some species, we cannot identify genus in the field like that. And even for family, sometimes we cannot identify. And all of the collection, for all the specimens, we made PowerPoint slides like this. And the first record is Shorea stenoptera. And the last one is Goniostyrus. And number 32 is a species of Rachianthus. This is similar to Rachianthus angustifolius, described from Malay Peninsula, but there are many differences. So this is a new species. And this is close to Bauhinia municipalmacea, described from Malaysian side of Borneo. But the type specimen of municipalmacea is described as having yellow flowers, but this has white flowers, and there are some differences. So I'm planning to describe this as a new subspecies of municipalmacea. So by using a 100-meter transect, this is a very short distance, but we could record 334 species, including some new species and new subspecies. And we made this survey in many locations of tropical Asia, and we are still going on. We are soon visiting another plot of Sumatra. And over the last 4 years, we accumulated about 20,000 specimens. For all the collections, we have DNA samples, and all are georeferenced, pictured, and the specimens are scanned. And in addition to field surveys, we worked on species distribution modeling in collaboration with Niels Rice of National Herbarium of the Netherlands. And he modeled, let's see, more than I think 5,000 species of 7 tree families, and overlaid them. And this is the result. The species richness is the highest in Sabah and Sarawak in Malaysia, and the species richness is lower in Sumatra and Malaysia, Malay Peninsula. However, in our transect survey, we recorded 396 species in West Sumatra. The species richness is as high as in Borneo. And also in southern Vietnam, there is a hotspot where we recorded 341 species. So it seems that this is, in this estimation based on distribution models, diversity in Sumatra is at least underestimated. Maybe that is because specimen density is quite low. So most specimens in tropical Asia is collected in Malay Peninsula and Sabah and Sarawak. So species richness may be underestimated in other areas. And we placed our plots in different locations of different altitude in many locations. And in Homba Nature Reserve of southern Vietnam, species richness is the highest at about 1,200 meters. On the other hand, species richness is the highest in the lowland in Sumatra. And this high species richness in the higher elevation is very interesting. Maybe this is the highest species richness in this elevation. In lowland Borneo, of course, species richness is the highest. It often exceeds 400 species, even within 100 meters. However, in swamp forest of Mandol, species richness is much lower. And what happens? In this survey, we found a lot of many new species. This is the case of Cinnamomum and Loresi. Those are general of Loresi. And this is the case of Fraser's Hill in Malaysia. This is a very famous place, very well botanized. We have many specimens in the herbarium of Malaysia. But even in Fraser's Hill, we found 4 new species of Loresi. And in the case of Homba, Vietnam, we recognized 28 new species compared with 21 described species. So on average, the proportion of new species is 37%. You may think that this is an overestimate. So I will show you the case of Neoritzia, a small genus of Loresi. In this, as for Neoritzia, 6 species are recorded in the tree flora of Malaya. 5 species are already described, and 1 is not yet described. And I visited Fraser's Hill of Malay Peninsula, a very well botanized place. And I found a new species of Neoritzia in 100-meter transect. This is a very unique species. Also, we recognized 4 other morphospecies like this. And to confirm the species status of those, we used sequence of ITS. This is ITS3. And you can see that this and this had almost identical sequence. And finally, we concluded that these are a variation of the same species. But this had slightly different sequence. And morphologically, quite distinct from those. This species has conspicuous tree nerve leaves, and veins are distinct on the upper surface, but are not distinct here. So we concluded that these 2 are different species. And 2 other species are quite distinct and also not so close to those species. And all the 4 species are not yet described. So we found 4 new species here. This is the case of Homba Nature Reserve. At first, we thought that those 3 are juvenile of this species, Neoritzia polycarp. And those are quite variable. This has smaller leaves, and this has larger leaves, longer leaves. But we consider that those are variation of the same species. And those are maybe juveniles, young trees of this. However, according to IT sequence, these sterile plants are distinct from this one. So this is not the juvenile of this species. These 2 are quite different species. So based on this kind of information, we recognized 44 species in our collection from northern Vietnam to Java. And among them, 25 species are new. So this is a situation of taxonomy in tropical Asia. And as for Loresi, maybe we need to describe more than 100 new species. And the situation is similar in some other big genus, big family, Rubiaceae or Myrtaceae and so on. And by using this kind of state data, we are going to we're trying to assess extinction risks. And we are working in particular on legume diversity because legume family, Fabaceae, includes many useful species, and it occurs from tropics to temperate, and it has a very important function of nitrogen fixation and so on. So there are many advantages of Fabaceae for the global assessment. And so we are constructing distribution models for many species. And also we are using land use change data for quantifying human impacts for each species. And our idea is that extinction risk is considered to be higher in species having narrower ranges and a higher human impact. So the species 1 should be critically endangered. On the other hand, those species are more safe. So we estimated, we at first modeled the distribution of rare species like this. This species is confined to northern Thailand. This is southern China and so on. This is a case of Bauhinia rayi variety Cardiophila. This is confined to Sabah and Sarawak. But based on distribution model, we can see that we can expect that this species can be found in West Kalimantan. And actually, we found this in Mandol Forest Nature Reserve. And so this is the estimate of species range and human impact index for Bauhinia and Dalbergia. And as for Bauhinia rayi variety Cardiophila, the range is quite small, and almost all ranges are under high human impact. So this should be a critically endangered species. In fact, this species is found only a small area of Mando Reserve, and almost all forests are now being lost in this reserve. So this estimation agrees very well with my experience. As for Dalbergia, those 3 species may be critically endangered. This kind of assessment is now going on for many species. And I think this is a good method for assessing extinction risks for many tropical species without any time series data. But the problem is that we could model only for a small number of species having abundant presence records, specimen records. As for Bauhinia, we could model only 90 species among 197 total. And among those species, 89 species have been known only from single locality. So there are many more rare species compared with widespread species. This is a very important fact. And we are interested in whether those rare or threatened species are phylogenetically clustered or not. And this preliminary tree for Bauhinia shows that threatened species indicated by red boxes are phylogenetically clustered. In this grade, there are many Asian species, but no species of those are not threatened. Only in this grade, threatened species are found. So maybe at least for Bauhinia, those species loss are so species loss means the loss of particular clade. So we need to assess phylogenetic diversity loss. A simple count of species loss is not sufficient for biodiversity assessment. So those are a summary of our achievements. We accumulated 20,000 records of distribution for all the life forms of vascular plant species. And we developed distribution models for more than 1,000 species. And the extinction risk assessment have been made on several genera of Fabaceae. But we are facing with some difficulties. First, taxonomy of many plant groups in tropical Asia remain to be revised, and we need to describe a lot of new species. So taxonomy is still a very important project in tropical Asia, even for tall trees. And larger parts of species are quite rare, often known only from single localities. So we need to make more efforts to identify those species in the field and assess extinction risks and the PD loss for those species. And another challenge is to barcode 20,000 samples. Unfortunately for plants, we don't have good markers. So we are now developing a new method of DNA barcoding by using next generation sequencers. But finally, I would like to thank all of those collaborators from various countries of Asia and in Japan. Thank you for your attention.
Thank you. Do we have perhaps a question for Dr. Yahara? Yes, Masha.
Hi, can you say a few more words about next generation sequencing as a new barcode?
Well, my collaborator, Yoshihisa Suyama, is submitted a paper, and I think that it will be published very soon. We are using SNPs. So we are using primers of microsatellites and amplifying various regions of genome, and that method is quite efficient to detect many SNPs, and then we can prepare some attachment. And by using those primers of microsatellite repeats, I think we can efficiently determine many SNPs for each sample.
Thank you. Sounds like a good subject for a working group. We've obviously gone a bit over. What I would like to suggest is that we break until 11:15. We'll reconvene here at 11:15. So please be back then and stay tuned for round two. The second half of our morning plenary session. It's my pleasure to introduce Dr. Rosemary Gillespie from the University of California, Berkeley, who will be talking to us about evolution of ecological communities through the lens of an island chronosequence. Thank you, Rosemary.
Thanks so much, Bob. And thanks to everyone for having me here. This is a tremendous pleasure, tremendous opportunity for me to talk about some of the work that we've been doing and hopefully trying to convince you of the value of a kind of model system for addressing issues in biodiversity science and for the use of the barcoding approach to do this. So just to start, I'm going to talk about a project, I'm going to focus on a project at least, that is a very large collaboration, NSF funded through their Dimensions of a Biodiversity program. And if I can get this to work. The two major players in the work that I'm going to talk about are Andy Rominger, who's a macroecologist, theoretical macroecologist, and Henrik Krehenwinkel, who's a genomicist. So what I want to talk about is really what the issues that people brought up this morning of biodiversity dynamics. We all want to see change over time, and we're limited in seeing change over time by our own lifetime. So when we look at biodiversity dynamics, the things we want to do are go up from microevolutionary processes where you're looking at lineages coming together and dividing and all sorts of things going on at the microevolutionary scale, and go up, scale up from that to macroevolution where things are actually diversifying. At the same time, we want to look at how evolution intersects with ecology. So evolution looks at exactly how things are connected over historical time. So how things are related, and you're always looking over the history. Whereas in ecology, you're basically looking at one point in time. You're looking at ecological metrics over space, but the time period is necessarily very limited. We're looking at very short temporal scales and looking at food webs and some really cool ecological approaches, but most of them are limited in terms of their temporal component. So what we want to do to understand biodiversity dynamics is put these two together and to use that to understand the actual dynamics of biodiversity. So what I want to try and see is how we can do this, because the processes occur over different scales, and so it makes it really hard to understand the dynamics. So what have people done? So just the ways people have used to get at this kind of problem is to integrate neontological and paleontological data. And this is just, these figures are based on a paper out of Catherine Graham's lab, where they looked at the dynamics of trait evolution. The blue lines are the extant lineages, the brown are where you include the extant and the extinct lineages. And the circles are the true and reconstructed trait values. And you see, when you include fossils, you get a much clearer picture of what the past what the lineage went through in the past. In the same way, when you look at species diversity through time, you can estimate species diversity through time based on extant lineages, but that gives you often a very biased view of what lineages actually exist, and you can get a better feel for that when you include fossil lineages. And likewise, when you look at the temporal dynamics of niche interactions, we often use niche reconstruction based on extant lineages and go back in time based on what we know of current distributions. But often when we include fossils, we get a very different picture. So that's been a very powerful way. Including fossils is recognized as tremendously important in understanding biodiversity dynamics. But there's another way to do this, and this is through the use of chronosequences. So this is what I'm going to focus on. an island chronosequence, and I'm going to focus on one particular island chronosequence because it's just a very beautiful one, and it behaves very well, and that's the chronosequence provided by the Hawaiian Islands. So what's nice about this is that in Hawaii you get a hotspot, which is just off the southeast coast of the big island of Hawaii. And so basically this hotspot oozes out lava, and as the plate moves away from the hotspot, the islands get older and eroded and eventually disappear. So you can use this chronosequence basically as a fossil record. So here you see 5 million years ago, Kauai was just forming, and these islands were low and far apart, and so they were actually, you can't do much with those older islands. Most things went extinct before they reached Kauai. So Kauai is kind of the first in the chronosequence of the current high islands. There are exceptions, I should say. So Kauai is the first, and Oahu came along. Things tended to jump from one island to the older island to the younger island. So the Maui Nui complex came along, jumped over there, and then you get Hawaii coming along, and they jumped over there. And so basically, you can use this almost as a fossil record, the oldest in blue, yellow, red, down to the youngest in turquoise. So you can basically read this as a chronosequence, as a fossil, read the chronosequence as a fossil record to look at the dynamics of trait evolution, species diversity through time, and temporal dynamics and niche interactions. So what I'm going to talk about then is microevolution, microevolution going to macroevolution. So evolutionary dynamics over time, species diversity through time, and ecological interactions over time. So first of all, let's look at microevolution to macroevolution, the very early stages in diversification. So for this, we're going to come to the youngest island of Hawaii. And I should apologize to Paul, much as he hates spiders. Much of this talk is going to be focused on spiders because that's what I'm most familiar with. But I should emphasize that all of the work we're doing is focused on arthropods as a whole. My particular focus is on spiders. So the work we've been doing to try and get at the microevolution to macroevolution stage focuses on the big island of Hawaii, where things are just starting to get going, and going over to the island of Maui, where you get clear defined species. So I had a student, Amy Vandergast, who built on work that Hampton Carson suggested on this very young island. Basically what you find is that the forest gets repeatedly carved out by lava. And as a result of this is a geological sequence on this young island. But if you look at this area here on this very young volcano of Mauna Loa, what you find is that it's very fragmented, naturally fragmented by lava. And so you get these little green patches are islands of vegetation. And what Hamp Carson argued was that these little fragments serve as a crucible for evolution, basically carving things up and allowing them to come back together again. So what Amy Vandergast did for her PhD was look at how well these fragments were separated by lava. So in terms of the organisms that were restricted to these fragments, were they separated? Were they genetically disconnected between forest pockets? And what she found, this is just mitochondrial DNA analysis, what she found was when forest patches are separated by lava, indicated by the red, you find marked genetic differences over distance. So this is the distance. When they've just got continuous forest connecting them, they're just the same across that entire forest area. So the bottom line here is that forest fragments repeatedly are fragmenting these populations. So they're limiting gene flow. So what we're interested in now is this balance between isolation and time. So what happens is the lava comes down, separates taxa, and then they come back together. Over time, they come back together. And coming back together is necessarily going to it's not enough time for them to become new species. But almost certainly the fusion is going to inject diversity in the same way as it does for cichlid fish at the beginning of our radiation there as well. So what we're interested in doing now is figuring out how this dynamic, this fusion-fission cycle plays out over time to generate diversity and adaptive radiations. So going on then from this, we want now to look at evolutionary dynamics. So basically, this is what people have looked at when they've used the fossil record. They've said, okay, the extant taxa show we can infer that this was their phenotype, this is their niche, but then when we include fossils, we get a different picture. So this is what they've done using fossil taxa. Now what can we do using the chronosequence? So let's just first of all think about what's going on with the chronosequence overall in Hawaii. So you've got the oldest island there, the youngest there, and there's a standard kind of dynamic that happens here in that most lineages progress from the oldest to the younger islands. Of course, there are exceptions, but this is a general rule. Now, let's just look at a few lineages as they hop down the island chain. This is one group, the genus Orson Welles, a sheepweb spider. And this is work by Gustavo Hormiga and Mikel Arnedo that they did a few years ago with me. And so what they found was that these species have jumped from the older to the younger islands. But let's look at how they've diversified. You see on the youngest island, just one species. Then on the middle island, this group here, there's a whole bunch of species. On the older island, more, and just a whole pile of them on the oldest island of Kauai. So basically, this group has undergone very little adaptive radiation. They've simply changed in geographic space and become new species. And they've just accumulated over time, just more and more species. Now, if we look at another group, these are crab spiders and the work of Jessica Garb. What she found on the oldest island, you get most of the lineages on the oldest island within this radiation. And you get much of the ecological divergence on the oldest island. And then all they did was hop down from the older to the younger islands, keeping their ecological affinities. So here's a pattern of diversification early, adaptive diversification early in the radiation, and the populations just hop from one island to the next, maintaining their ecological affinities. So then come to just one more pattern that you find. This is the genus Tetragnatha that I've done a lot of work on. And this is a huge radiation of super cool spiders. And this is one group, the spiny-legged species that run around. They're active cursorial predators. How have they diversified? When you look at them, the oldest island going to the youngest, so they've hopped down from the older to the younger islands. But here, I've marked ecomorphs. These are very distinct ecological forms, the green ones, the brown ones, the maroon ones, the big brown ones, that have evolved repeatedly over this time frame of the Hawaiian Islands. So independent evolution of ecomorphs. You find exactly the same thing in these stick spiders, the genus Ariamnes. So what they've done, and you can't read this too well, but the point here is this is Kauai, where you get a brown and a gold ecomorph, Oahu, where you get independent gold, white, and brown, a whole bunch of them within the brown, gold, and white ecomorphs on Maui, and then just a couple of populations on Hawaii. So then how does this work in the context of a chronosequence? So just to explain, because sometimes it's hard to relate what we're trying to do with the fossil record with a chronosequence. But basically, here's what you're trying to do with the fossil record, get a more accurate picture of the deeper nodes. In a chronosequence, in an old chronosequence like Hawaii, we're looking at the oldest island, and here you see the extant representatives from that old lineage. But then it reset itself. It went to the next island, and reset itself. And so it started again. And here you get to these 3 species based in that time frame. It went to the next youngest island, reset itself, and evolved all of these different taxa again. And then to the youngest island, where you just get populations appearing. So it gives you a sequence of change, basically a resetting of the lineage, so that you can see what happens in the early stages of the lineage and later and later and later. So what we can see based on this then is that taxa differ in the interplay between ecological and genetic shifts during diversification. So what we can now do is look at patterns of diversity over time across whole communities. So if you look at the taxa that I've just been talking about, this is the fossil record, and how the information from extant lineages in the blue is much clarified, you get much more information by including the fossil record. Let's look at the chronosequence and see what we find. Here is the species per unit area of the spiders I've been talking about. The Orson Welles, the crab spiders, and these are the Ariamnes, the stick spiders, and the Tetragnatha. And you get very different patterns over the chronosequence. So some of them just increase just forever to the oldest island, the Orson Welles. Some very quickly reach a peak and then just stay steady. Some seem to reach a peak and die down. And these are the ones that undergo the repeated evolution of similar form. You find that across lots of different taxa. This is all sorts of different animal taxa in Hawaii. You get the more diverse lineages showing a peak of diversity on the middle-aged islands and then dying down. And the smaller lineages keeping diversifying, keeping increasing. So relating this, the fossil, what they're doing with the fossil data, what you do with the chronosequence, what we're finding is different lineages show different patterns. Some just increase over time, some increase and then level off, and some show a peak and then die down a bit. So what we can say then is that taxa differ in the interplay between ecological and genetic shifts during diversification. We've seen that. But the rate of accumulation of species and the patterns of diversity over time are different for different groups of taxa. So this highlights that different groups perceive the chronosequence differently. And what we can do now then is look a bit in greater detail at ecological interactions. So we can actually use the chronosequence to give a temporal dimension to the explicitly spatial ecological theories that have been developed. So for example, here you see, this is where they've used the fossil record, what we talked about before, to look and see what distributions of the ancestral taxa in the fossil record were and how the current taxa relate to that. How then do we use the chronosequence to do that? So what we've done here is we're using this, a tool that, one that's been finessed really by John Hart, who's a collaborator in this work. And John uses an approach, the maximum entropy theory of ecology, not to be confused with the niche modeling use of this approach. But in this, what he's called MET approach, what he can do is just basically look at communities and develop metrics of abundance, diversity within those communities based on statistical properties of the communities. Basically, what it's doing is generating a null expectation. If no biology is going on, what kinds of distributions would you expect? In short, what it's basically doing is taking the energy of a community and packaging it most parsimoniously into individuals and then into species. So this allows us to look at community-wide patterns across the chronosequence and testing of this theory across the chronosequence. So here you see, based on very preliminary data, these are for detritivores, across the Cronus sequence. This is the oldest island, and this is the youngest. The black line indicates the predictions from the maximum entropy theory, the black across here, and the circles are the actual data. And what you can see is that you get the highest deviations from the maxent predictions on the youngest lavas. So the deviation from the predictions on these youngest sites may indicate that the community hasn't reached steady state. All this is saying is that this is something to look at. It's not behaving normally as normal communities behave. Now, you can do the same with interaction networks to see how predictable change is over this time period. So what we've done so far is look at modularity and nestedness. We've developed just a bipartite network for leafhoppers and just generated these networks and tested them across the Cronus sequence, looking at how modularity and nestedness change across the island chronology. And what you see is that nestedness decreases with age, perhaps due to the high immigration of new species with high probabilities of eating or being eaten by generalist species already present. And then modularity increases, likely due to coevolution on the oldest island. Now, so this is just basic food web metrics. You can also apply the maxent theory to these kinds of interactions. So using statistical theory to say whether you get statistical deviations from the expectation of food web interactions. Again, using the leafhoppers and the plants. And so here again, the red line here is the expectation based on the maximum entropy theory. The circles are the actual data. And what you see is that you get this is statistically not significant when the red line falls in the gray. And what you find is that they statistically deviate from the predictions on the very youngest island, probably because assembly hasn't really got going. And then there's another deviation on the oldest island, presumably because you get ecological specialization. So these are both indicating that networks deviate from statistical predictions based on these sites. So what we can say then at the moment is that across the Cronus sequence, different arthropod groups perceive, colonize, and diverge across the evolving landscape differently. And this results in different patterns of species accumulation over time. You get deviation from statistical steady state that varies across groups. And the interaction of ecological and evolutionary strategies, isolation and mixing, likely interact to produce the patterns that you see. So as we end here, what I want to just tell you a little bit about is what we're doing going forward using this Cronus sequence. So we've got a team out in Hawaii at the moment working across this Cronus sequence, the oldest island, and these are the actual sites that we've got. So we're looking at lavas of different age from the very oldest to the very youngest. I should say just here that we're looking at sites that are standardized as much as possible with a similar elevation, precipitation. They're all metrosideros forest, and they're all accessible. What we do in those sites is we collect the bejesus out of arthropods. We're using very quantitative approaches to get actual numbers based on multiple sampling methods. We don't use lures or anything like that. We're just looking, we want to get numbers of arthropods at a given site. And so we use things like malaise, beating, litter samples, and multiple other techniques. So what we're wanting to do then with that data is to look at everything across the Cronus sequence. We're trying to get at biodiversity dynamics. And when you look at biodiversity dynamics over time, you want to get everything. So this is really what Henrik Krahenwinkel is pioneering here, looking at at metagenomics across the Cronus sequence. So what he's doing is trying to develop an approach that allows you to look at change in the evolutionary dynamics right across the chronosequence. So looking at the genetic structure of all the lineages in the ecosystem, and which factors drive divergence in lineages. So which ones separate first and which ones follow after the others. Do bacteria diversify and are they driving the process, or the fungi, or is it the interaction, or is it prey that start and then predators? What exactly is going on? And at the same time, what he's trying to do is get the data to give you actual abundances. So get rapid identification of taxa, because you get far too many, and look at relative abundance and use metabarcoding of whole predators to identify prey-predator interactions and food plants of herbivores, which will give us a much more precise indication of food-web interactions and how these are changing over time. So the multiple approaches that he's using, these are all in development at the moment, and I think you're all very familiar with the approaches that he's trying to pioneer. Basically, looking at everything, using all the tools available to him, and building on work of many others. So this is the work that's actively in progress, and I think it's a very exciting time to be using this kind of data to understand, to actually get a feel on how lineages change over extended time periods. And with that, I just want to say thank you, and I'd take any questions if there's time for any.
Thank you very much, Dr. Gillespie. Do we have any questions?
Just curious about genetics amplicons. So I see that you're doing amplicons on the one hand, or are you doing also whole genomic shotgun sequencing? And
so we're, for this approach, and I should say that I'm not, this is Henrik's baby, and I would hate to try and say what he's doing, but no, this is just, we are doing shotgun sequencing, but in this one, we're more interested in the entire community. So we're just using the metabarcoding approach to look at all of the species in that. All of the species, the numbers of those species, and the diversity of species in that entire community.
Thank you. One more question.
Very nice talk. I was just wondering, how did these spiders move from one island to the other? And did they ever go backwards to the older islands?
That's such a great question, and it's really interesting. So in general, no, the spiders are very good at doing the older to younger island. Some groups that seem to disperse more, like Drosophila, the flies, the moths, some of them tend to go back much more. And I should say that what we're doing here capitalizes on these specific attributes of the system. First of all, that it's by and large closed. So that very few things come from outside, so you know what you're dealing with. There's a big issue that, of course, I'm glossing over, that why is the invasive species capital of the world? But fortunately, or whatever, at least for now, the invasives are generally low and the endemics are high up. And so you can use that to look at the native species and hopefully ultimately look at the interaction between the native and the invasive. But the bottom line is that the native species show this, they tend not to move, at least for spiders, are just tend to move very little and show this pattern of older to younger islands.
Thank you. I have one quick question. I'm curious about, is there another up? Wait for the mic. We can't hear you then.
Hi, I'm just wondering if you've noticed different patterns of spider dispersion, like from the different families, because are they mostly ballooning to disperse, which is like a passive way? And would that be affected by like weather? Because you'd be saying they're they seem to be dispersing from older to newer, but not the other way around. But I'm just wondering how that would be, because they're not really controlling the direction, right?
So the dispersal, so spiders do disperse by ballooning. These spiders, all of these families are well known for ballooning. I've never seen them balloon in Hawaii, and the areas of endemism that we're talking about here for many of these groups are remarkably tiny. So levels of endemism generally, they increase from younger to older islands. So when you get to the older island, things are often doing fine, but endemic to areas not much bigger than this building. So in terms of ballooning and their movement, it seems to be that they just simply don't move very much.
Thank you. In the interest of time, I think I'll save my question for the break, and we'll move on to our next speaker. I'd like to introduce Dr. Melania Cristescu from McGill University, and we'll get you mic'd up and on our way.
Can I? Let's see. Oh, it's not working. I will hold this like this tight. The PowerPoint, but no, the PDF. Sorry, you can. It's holding. No? Okay, I think it's thing. Can I control it with the? So this is. Okay. So it's going to work even if I have it on the PDF. Okay, thank you very much. Yeah, okay, works. Yeah, good. Thank you. Good morning, everybody. And I would like to first thank the organizers for the invitation. It is a tremendous opportunity to be here. And I also would like to thank all of you for being here with us. So today I'm going to talk about sequencing our ways towards understanding and managing invasive species. As it is all well appreciated, this continual destruction of natural barriers due to increased global trade and human travel generates this massive biotic exchange between previously isolated regions and generates what we call this global biotic homogenization. Many ecosystems are dominated by non-indigenous species, and often these species have invasive traits that allows them to spread quickly and to also change the dynamic of invaded ecosystems, change species interactions. So this is particularly prevalent for the aquatic ecosystems. The major ports of the world are massively interconnected, and this is mainly due to the shipping traffic. So these ports receive massive amounts of ballast water and fouling organisms, and they often represent the entry points for non-indigenous species, thus our interest in studying these particular environments. But for now, I'm going to step back a little bit to introduce the problem a little bit better. So here are examples of notorious aquatic invasive species, and they have this bad reputation, as my title suggests. And this is because they have strong ecological and economic impact. And we spend lots of resources trying to sometimes eradicate them, but like often just to slow down their secondary spread. However, we learn from these experiences that they are particularly resilient. Yeah, they represent nothing more than successful evolutionary stories, yeah, evolution in action. Species that constantly adapt to a changing world. And certainly there are important lessons that we can learn from biological invasions about the ecological footprint of our own species. So Elton's book, The Ecology of Invasions by Animal and Plants, was perhaps the first firm warning about an imminent ecological crisis. Yeah, he described the world as a very explosive world in which we don't know when or where the next outburst will be, but we might hope to find ways of stopping it, or at any rate, damping down its force. So with incredibly wit, Elton recognized this high level of endemism, regional and continental endemism, the continual destruction of natural barriers. Few years later, and precisely half a century ago, the influential book on the genetics of colonizing species, edited by Stebbins and Baker, was the first to place biological invasions in an evolutionary context. So the authors explore the changes that these species undergo as they enter a new ecological space or a new geographical area. Now, 50 years after, the field of biological invasions is going through massive transition, and more we use these molecular tools to understand biological invasions, and often we use barcoding and meta-barcoding tools. So we use these tools to look at the identity of aquatic invaders and ask the question, who are these invasive species? And although these might look like a trivial task, in many cases their taxonomic status remains unsettled. We use also these tools to look at the evolutionary and invasion history and understand their native ranges and the sources of introduction. We try to also understand how they travel around the world, their vectors of introduction or vectors of secondary spread. Do we deal with single or multiple introduction events? And we use also population genetics or population genomics approaches to look at their colonization dynamics across invaded areas, look for signature of bottlenecks, or look for other evolutionary events, such as hybridization with native taxa, inbreeding, selective sweeps. So ultimately, we are interested in causes and consequences of invasiveness. But from a more practical point of view, and more recently, we can embrace barcoding tools to look for the early detection and preventing measures of biological invasions. So to give you a little bit of a feeling of how the work goes, during the first phase of the Canadian Aquatic Invasive Species Network, our group was involved in studying several invasive ascidians that had a major ecological effects. They have a global distribution. So here are a few examples of species that are commonly found along the North American coast. The colonial golden star, and violet tunicates, as well as the solitary vase tunicate. So these species can be found in huge aggregations on both natural and artificial substrates. So they spread rapidly, overgrowing almost all sessile species in this process. Now, the reason for this massive proliferation and rapid expansion is not well understood. However, it is believed that eutrophication, or pollution, dredging of the substrate, overexploitation are possible causes. So one of the first species that we investigated was the golden star tunicate, Botryllus schlosseri, which is considered to be native to European coastal waters and reached global distribution during the last 2 decades. It has a very strong impact on aquaculture facilities due to its ability to blanket and suffocate entire mussel lines, as in this picture. So as I mentioned earlier, so Botryllus is known to have a native range in Europe. However, this is mainly an educated guess. All we know is that this species reached global distribution during the last 2 decades, is found on most continents and major coastal zones. So our former student Dan Bock looked at the invasion genetics of Botrytis loseri using both nuclear and mitochondrial markers and phylogenetic and population genetic approaches. So this is the phylogeny, mitochondrial-based phylogeny that Dan recovered, and this suggests that Botrytis loseri is actually a complex of cryptic species. While one of these species found here in blue is highly invasive and was identified on all continents and coastal zones that we looked at, these other closely related species represented here in red and green have a very narrow distribution. They are found only along the English Channel. Now you might be wondering if this genetic break, nice genetic break, represents biological species or reproductively isolated units, or they simply reflect genetic breaks due to historical barriers to gene flow, historical barriers. So when we're asking such questions, nuclear data can be very handy. So in this case, nuclear data based on microsatellite markers fully supports this mitochondrial phylogeny. So this is a Bayesian structure analysis with full support for 3 main groups that fully correspond to the mitochondrial clades. So in this diagram, each fine line represents a multilocus genotype, and the color code corresponds to the probability of that multilocus genotype to belong to its group, one of the 3 identified groups. And this is a very simple diagram because it reflects that most multilocus genotypes show almost 100% probability of belonging to their own group. And this was true also for populations in which these closely related species come in symmetry, like in this diagram. So you see members of the 2 clades here coming in symmetry. There is no evidence of nuclear gene exchange, suggesting reproductive isolation. So these clades represent biological species. And this is important because such data sets allows us to explore the extent to which distributional ranges are phylogenetically constrained. Do closely related species show similar distributional ranges? And the answer appears to be no, at least for invasive species. We recover similar pattern in other invasive ascidians. So one question that these findings raise is, why do some species proliferate at an alarming rate while their closest relatives are facing extinction? Is this due to the competitive exclusion, one species being a better competitor than the other, due to the stochasticity of the invasion process, some species having access to vectors of dispersal and secondary spread? Or is it simply due to fine-scale adaptations that perhaps ecological genomics approaches can identify? But right now, I'm not going to go deeper into this question. However, I want to just suggest that these patterns of closely related species with different distributional ranges and different dispersal abilities pose a great problem when we try to identify invasive species. And I'm going to switch gently the gear now to look into the early detection of high-risk aquatic invaders in the Canadian ports, like both freshwater and marine ports. As most of you know and appreciate, these days it's very simple to combine the use of traditional barcoding approaches with next-generation sequencing to describe complex communities and to also identify invasive species. It's what we call meta-barcoding. And with this procedure, we sample complex, so we get complex samples, as in our case, zooplankton samples. We grind entire samples and we amplify a particular marker of interest. In our case was the 18S marker. We obtain millions of sequences, we filter them, then we cluster them using different analytic clustering methods, And then optionally, we, when necessary, we blast representative sequences of these OTUs to describe these complex communities. So the method is very promising, however, has also problems that have to be worked out along the way. And for this reason, we try to validate our methods using a series of mock communities. So we assemble both very simple and more complex communities. For example, this is an example of a simple mock community in which each of the 20 species that entered in this community was represented by a single individual, generally non-brooding, and individually labeled. So this allowed us to look at the level of intra-individual genetic variation, if any. And then we assemble more complex communities in which each of the 30 species that enter into this community was represented by multiple populations, both population of small numbers and more abundant populations. And with this approach, we are able to look at the level of intra-population genetic diversity. So using this combination of mock communities, we are able to explore a number of questions. We look at first at the impact of intra and interspecific diversity to our ability to recover OTU numbers that correspond well to species richness. So we found that simple communities, the ones based on single individual per species, generated a generally high correspondence of about 60 to 84% between the OTU number and the species richness. However, when we went to more complex communities, when we examined them closely, we noticed that the correspondence dropped to about 30 and 63%. We investigated this further and we found that intraspecific and sometimes even intra-individual variation in our 18S region exceeded the 3% divergence. And you think that the solution is simple, we can simply adjust our threshold. However, we found that at the same time, many closely related species show less than 3% divergence. So we clearly had a problem that we had to overcome. Another element that aspect that we were able to investigate using our series of mock communities was looking at the effectiveness of different methods of clustering, different analytical procedures. So we use a combination of stringent and relaxed filtering with singleton sequences included and excluded. So if you don't remember, singleton sequences are those very, very rare sequences that you capture only once in your sample. We also use 3 different clustering algorithms, the ones that are commonly used in the literature, MOTHER, UCLUST, UParse, and also use different methods, 3 distinct methods of treating alignment gaps. So we investigated all these analytical procedures and we found that the number of OTUs varied by nearly 3 orders of magnitude when working with these different analytical approaches. We found that the use of relaxed filtering and the inclusion of singleton greatly inflated the number of OTUs. At the same time, the methods of treating alignment gaps had a strong impact on our estimate. So after going through these validation steps, we felt a little bit more confident in going and exploring the spatio-temporal zooplankton biodiversity trends across the 16 Canadian ports. So the Canadian Aquatic Invasive Species Network had a sampling team that managed to sample 16 ports across 4 geographic regions: Atlantic, Pacific, Great Lakes, and the Arctic. So 4 ports per region. Each port was also sampled at 4 different sites across 2 seasons and with 2 different plankton nets, different sizes. So it's a big sampling effort that was involved in this project. Now, in order to try to overcome the problems that I just mentioned that we encounter with this particular marker and with particular data set, we use two different methods of analyzing our data set. So we use the general clustering approach that I just mentioned, so to generate the OTU clusters. However, since this method requires quite a good, reliable barcoding gap and accurate divergent threshold, which we didn't have, we use another complementary method that we call a taxonomy dependent approach. So in a simple way to put it down, this involves blast searches of individual reads against local databases. Yeah, so this method requires a well-developed reference library and certainly the concerted global effort. And it also depends on a local database to make it computationally feasible. Yeah, so it requires a customized pipeline specific to the marker and taxa of interest. And the taxonomic extension is at the core of this approach. So new resolution depends on the local database. The results that I'm going to report are based on this method because we found that it provided us much higher resolution and accuracy. So these are the major highlights, and I'm going to go into this point by point later on. But for now, I just want to mention that we analyzed 7 million sequences, and more than 90% of them were assigned, taxonomically assigned. However, only about 50% of these sequences were assigned at the species level. Regardless, we managed to identify species spanning 392 metazoan families over 105 orders. And these families complemented previous survey based on morphological identification. We also revealed species from over 30 orders that were not previously reported that we are investigating now closer. We also found, as you would expect, that certain taxonomic groups were underrepresented to the incomplete reference database that we had to work with. And again, as you would expect, zooplankton communities were very distinct among coastlines and also among habitat types, marine, freshwater, estuarine. We found a little bit unexpectedly that biodiversity varied substantially across seasons, particularly for the subarctic region, with Churchill showing very high seasonality, not only in species composition, but also in abundance. And we also revealed a large number of non-indigenous species, with many of them report in unreported regions. So 20% of the species that we looked for, we managed to identify. So now I'll go a little bit slower, step by step. So this is a proportional abundance of phyla that we identify across samples, like all the 16 ports. And you would see that, you can see here that most of the sequences, more than 90%, yeah, belong to crustaceans. And this was intended because our primers are intended to amplify crustaceans. We also amplify annelids, ctenophores, mollusks, and from time to time we amplify also groups that our marker were not intended to actually recover. If you go at the finer taxonomic level, at the family level, here you can see the proportional abundance of family across samples, with each column representing a port of the 4 regions that we investigated: Pacific, Arctic, Atlantic, and Great Lakes. So this diagram is a little bit difficult to digest, but the take-home message here is that the most abundant families that generally belong to copepods are also shared among ports within a particular geographic region. Now, a little bit more intuitive is to look at the PCA, principal component analysis of samples, based on at the family level based on presence, absence. And here you see the strong grouping. Each dot in this diagram represents a particular site or season in a port. So all the samples in the Great Lakes are here in greenish colors, and then in red, the Arctic ports. Then with the blue Pacific and purple Atlantic, you can see that the Bayside port form a clear cluster, very distinct cluster, because this was the only port that has a true estuarine environment. And for the exercise of identifying invasive species, we use our specific approach of blasting individual sequences in order against a local database that included 125 non-indigenous species. We identify 25 of these species, so we identify about 20% of the sequences that we enter in our database. Most of these non-indigenous species were recovered in the Atlantic ports. So this afternoon, our postdoc, Frederick Chain, is going to continue this story about our exercise of identifying invasive species. So if you are interested in our protocol, in the way we validated this methodology, please join his talk around 4 o'clock in the biosurveillance session. Now, before closing, I would like to tell you a few words about the things that we learn from these projects and from working with 18S sequences. So clearly the metabarcoding approach is very sensitive if applied appropriately. We still have major steps to do to go to further advance this methodology. We greatly need reference libraries that incorporate reliable taxonomic information. There is no question about this. We also need comprehensive databases of invasive species. We made a good start here, but there is a lot of work to be done. We also need methodological validations. More of these validations are needed using more communities to calibrate our estimates. We also, I think, need to make this transition to multi-marker approaches. And if you'd like to see the progress we are making towards this approach, I invite you to join the poster 15C or C15 that our master student Guang Zhang is going to present on Wednesday. And of course, we need to continue to promote standardization and reproducibility of metabarcoding approaches. And all this can be only done to a global coordinated effort that integrates traditional approaches and effectively implements the emerging technologies. So I would like to send a big thank you to my long-term collaborators as well as to my enthusiastic lab members that always bring on board the unexpected element of the research. Special thanks to Julian, Emily, Freddie, Guang, Eben, so they ultimately run this research. And I would like to thank the funding agencies. Thank you all for your attention. But before I'm closing, I would like to extend my thank you to Paul Hibbert and his enthusiastic team at Bio for making barcoding a Canadian icon. And to close this picture, I would like to invite all of you to consider the NRC Canadian Journal Genome as a destination for your exciting research. Thank you very much. I'm happy to take questions.
Thank you, Melania. Do we have any questions from the audience?
Yeah, there is a question over there. Yeah. I think I can.
There's a microphone coming. Please use the microphone.
Now you hear me? Okay.
Yes, much better.
I would like to go back to the fascinating story of Botrytis schlosseri, the tunicate.
Okay.
And the different, the three clades that you designated over there.
Oh, yes.
It is possible that at least one of these clade is a complete known another species that was not recovered when the material was collected. So it could be that by doing collections all over the world and depending on the collector's knowledgeable taxonomy, we can introduce error in barcoding of different species. This is one example. We also collected, we have now more than 800 samples from all over the world. And we found that at least in one of these clades, we have 5 clades of Botrytis.
Okay.
And at least one of these clade, which correspond to one of the 3 clades here, is a complete different species. By giving it to taxonomists, then you find that this species is not the species that we thought about. So it is. I'm just raising this note that because we should be very careful when we collect animals or plants and identify them as species A or B.
Yeah, this is a very important point because the problem of closely related species in which one is is becoming invasive and other are close to extinction might be a common pattern. We found that for Cyona intestinalis as well. Yeah, there are two species that are highly invasive. However, there are many other species into the Cyona intestinalis complex that have very narrow distributional ranges in the Black Sea, Mediterranean Sea.
Thank you for a great talk, Melania.
Thank you.
I mean, from your here.
Okay, good.
Yeah. So from your mock, I guess, could you comment globally, like from your mock experiments, basically you commented depending on the criteria and so on, depending on the complexity of the assemblage. I mean, things could vary tremendously in terms of what you would get, like you talk about 3 orders of magnitude and that sort of things. So could you comment generally, so I get at the end of your talk, I wasn't sure we should be hopeful or not in terms of the reliability of applying metabarcodings to document community patterns.
Yeah, personally, I'm very hopeful, but I'm also fully aware that we have many problems, and they could be marker specific, taxon specific. So we have to be very careful when we go to select our pipelines or select our methodology, our approach, because in some cases, for example, we found that clustering might not work for us if we want to get to fine level resolution to identify invasive species, and that the blasting of single reads might take us much farther. So ideally, we like to go back to work with the Koan marker, like primers, like to work with the Koan marker because the database is so much better represented. So that is going to give us much higher resolution. So we are making a big effort in trying to overcome the problem of having to, having difficulties amplifying certain groups. This is the major problem that we encounter when we have communities that are very complex. Yeah, you have to use multiple primer pairs. So that is what we try to develop these days.
Okay. Thank you.
Thank you very much, Melania. All right, our last speaker for this session is Dr. Thibaut Decans from the University of Montpellier. He'll be talking to us about dissecting tropical earthworm biodiversity patterns in tropical rainforests with the use of DNA barcoding. After this session, after our last speaker, we'll have a few housekeeping details and break for lunch.
Thank you. So first of all, I would like to thank Paul and Merdad for inviting me and all the organizing committee of this meeting and give me this opportunity to present you some results of an ongoing project we are conducting in French Guiana, which aims at analyzing earthworm biodiversity in tropical rainforests using DNA barcodes. So first, I would like to start with a broad overview of a few reasons why, in my opinion, it's important to study soil biodiversity, and especially invertebrate diversity in soils. So soil invertebrates has been attributed a number of values. They are regulators of important soil processes. They are implicated in the maintenance of soil fertility in agroecosystems. And they are also of strategic importance because they comprise very rich communities in terrestrial ecosystems. They also comprise a few invasive species of economic and ecological concern. And they are now widely used as bioindicators of soil quality and pollution. So they are also practically important in biomonitoring studies. A number of studies highlighted the importance of soil-animal diversity for ecosystem functions. Different species perform differently in ecosystems. Functional diversity, in particular, is very linked to important ecological functions such as organic matter decomposition, the maintenance of soil structure, etc. And there is growing evidence that global change can affect soil biodiversity and the production of related ecosystem services. So it is critical now to understand the dynamics of these communities and try to at least predict the impact of biodiversity erosion on these ecosystem services. In this slide, you can see the main taxonomy groups of soil biota ranked along a gradient of body size. And this illustrates first the high taxonomic diversity of soil biota, with species ranging from bacteria to vertebrates, but also the very high diversity of life forms and body sizes. And this means that, well, two important points. First, we have no method to sample all biodiversity in a given soil. And second, there is probably no specialist in the world that can identify readily to species level, all the organisms that are contained in a single sample of soil. So these are two important points. As many other groups of invertebrates, soil invertebrates are characterized by a high taxonomic impediment, meaning that the known biodiversity is only a small fraction of the real diversity. And this taxonomic deficit is higher for groups of small species. And altogether highlight the difficulties for studying soil biodiversity. So we have a high number of species. We have high level of expertise required to identify these species. Many species are small-sized with minute characters, a high phenotypic plasticity, and non-diagnosable life stages. For example, in a given sample of earthworms, you will have almost more than 60% of juveniles that you cannot identify to species level just with morphology. We also have a deficit of taxonomists, legacy issues, and for these reasons, we have problems for establishing reliable lists of species and also to establish the taxonomic status of important biological models. Now, what about earthworms? Earthworms are present in most soils of the world. They represent the dominant component of soil faunal biomass in many ecosystems where they are present. And to date, we described 5,500 species, and we are almost completely unable to estimate the proportion that this number can represent compared with the real diversity of this group. Here you can see two classical morphs of earthworms. These are two European species that are now invading most of the temperate soils in the world. But just let me show you a rapid sample of earthworm diversity. Well, we have very big species, giant earthworms from several meters long, and colorful species, mostly in the tropics. So it's a group that is more diverse than just this kind of morphological features. Well, DNA barcoding in earthworm studies help us getting rapid identifications, species discrimination. We can link juveniles with adults and obtain species identification for juveniles. And we can also detect cryptic diversity in communities. And conducted at a community scale, DNA barcoding, we can delimit molecular operational taxonomic units that are further used as species proxy to describe diversity patterns or diversity level or community patterns at different scales. And this is especially important and useful for tropical ecosystems that have been poorly studied. So in the tropics, we still know very few about earthworm diversity and distribution. And just an example, in French Guiana, a checklist published 3 years ago stated that there was 22 species of earthworms. And this is obviously a very low number. It was just the state of the art at that moment. So this illustrates the lack of study on this group in this kind of ecosystems. So our project aimed at building a library of DNA barcodes for earthworms in French Guiana and use these molecular data to explore community patterns at different scales of space. Here is the sampling design. In red are all those sites that were sampled and for which we already have molecular data. In green, sites that were sampled very recently or will be sampled in the nearby future and for which we don't have these data, but we will have them in the further months. In each of these sites, we selected, we worked on a selection of representative habitats. We tried to have at least 3 replicates per habitat, and in each of these replicates, we did hand sorting of 3 standardized blocks of soil, and then 2 people during 2 hours search earthworms in 1 hectare area in all available microhabitat. This was a kind of qualitative sampling. And we search earthworm in soil, litter, decaying logs, but also in epiphytic soils, which are those accumulation of organic matter you can find in epiphytic plants or hollow trees. I cannot resist to show you a few pictures of these beautiful sites where we were sampling. But this also illustrates the diversity of the habitats that we prospected. So we sampled earthworms in rainforest on well-drained soil, in periodically flooded forest, in forest on white sands, but also in the savanna-like vegetation of these Inselberg mountains in a few sites. Specimens were fixed in pure ethanol, separated in the lab into morphospecies, and we kept a selection of 5 specimens per morphospecies per sample for DNA barcoding, and CO1 was sequenced. Part of the samples were sequenced using Sanger, and another part using MySeq technology with the tag primers to keep the link between the sequences and the vouchers. Using a subset of the data, we identified the barcode gap at 14%, which is very high compared with what is usually used for arthropod, for example. But this is congruent with the interspecific divergence we found in using temperate lumbricid earthworms. So it was quite congruent with the other studies. And we used this threshold to delimit motifs and used these motifs to estimate species richness and describe community patterns. So we had in total more than 2,500 barcodes obtained from separated vouchers collected in 7 different locations. And in total, we obtained 148 motifs with a very good match with morphology, at least for those specimens that were examined for morphology. Most of these species, probably 90% of these species, are new for science. And obviously, this is a dramatic increase compared with the 22 checklist that was recently published. This illustrates first the high taxonomic deficit that characterize earthworm communities in these tropical ecosystems, but also the added value of using DNA barcodes for a rapid survey of earthworm biodiversity in such ecosystems. Just to focus on one site in the Nurag reserve, we obtained 48 species level motifs belonging to 5 families and 12 genera, with a very good match with morphology, except in a few cases. So this is the highest local richness ever recorded worldwide for earthworms. And it was interesting to find in the same locality coexistence of most South American families of earthworms, but also some clusters of diversified but very closely related species. So this suggests that the high diversity that we are observing in this ecosystem could be explained by both the museum hypothesis and the evolutionary cradle hypothesis. Obviously, our sampling was far from an optimal situation. You can see on these accumulation curves that none reached the inflection point. And we had a high number of singletons in the data sets, almost in every site more than 20%. And local richness ranged from 11 to 57 species level motifs. So this was a very high diversity. Anyway, in every site we found a very high diversity of earthworms. But maybe the more interesting result of our study that 90% of these species or motifs were found in a single locality. So we had a mean pairwise Sorensen dissimilarity index of more than 80%. And when comparing all the sites in pairwise comparison, each together, we never found more than 20% of species that were shared between 2 sites, except in one case, which was the 2 locations of the Nurag reserves that are distant from only 12 kilometers, while the other sites are very distant. So this suggests that there is a kind of relationship between distance and beta diversity in these communities. Although this was not really supported by statistics, so probably there is other factors that can be used to explain this high level of beta diversity. What about regional diversity? Here is a rarefaction curve obtained from the world data set. And you can see that it's more like a straight line than a curve. And when using the CAO1 index to estimate regional diversity, this gives us more than 300 species for the world region. But probably we need to get more sampling to have a better estimation. But this just says that probably we have several hundred species of earthworms in French Guiana. Now we can use these barcodes to go deeper into the community structure in a given site. In Saül, for example, we sampled 3 different types of ecosystems: hilltop forest, slope forest, and periodically flooded lowland forest. And we found that species richness was lower in lowland forest than in the other 2 habitat types. And with the alpha diversity patterns that were identical between slope and plateau forest, with the rarefaction curves that were completely overlapping between these 2 kinds of habitats. When comparing the composition of the communities, we found that slope forest and plateau forest had very similar, quite similar composition compared with the lowland forest. But we also found that a high percentage of our motifs were found in a single type of ecosystem. So this suggests maybe undersampling, but also probably the importance of specialist species in these communities. And this was further supported by a more specific analysis we made with the Nurag data, where we looked at the distribution of motifs among microhabitats. And we found that most of these motifs were found in a single type of microhabitats, with only 4 of them here that were found in the 3 main types of microhabitats. And when looking just at those species living in surface microhabitats, these species seem to be able to use indifferently litter layer, decaying logs, or epiphytic soils. In the nurags, we found 17 species in the trees, in these epiphytic soils, but only 3 of them were found only in these microhabitats, and 2 were singletons, and the other one was found in a single bromeliad, so it was a single population. So this suggests that these species are more opportunistic species, just dispersing horizontally and vertically. They are just climbing into the trees, taking advantage of the high humidity, and looking for different habitats. And we found earthworms up to 40 meters in these epiphytic soils. We found them in bromeliads, but also in other epiphytic plants, and even in these flowers of heliconia. So they seem to be able to climb into the stem of the flower to go to eat the decaying organs of the flower. Now we can also use our information to describe the ecology of each of these species level motifs. Here is the vertical distribution of one species of the Nuraghesia genus. And you can do this for all your species, and then you can use this information together with a morphological description to build a table of functional traits and start to go deeper into the functional structure of the communities. Here we used all the motifs. We use a table of functional traits to make a functional classification of all the motifs that were found in the Nurag habitats. And we discriminated 4 different groups. One is a group of large to very large species, usually pigmented, that live in the soil and in the decaying logs. Then we had 2 groups of species living into the soil. One is of species with the cutaneous pigmentation that live close to the surface, and the other one, non-pigmented species living deeper into the soil. And the last group are small, usually pigmented species living in decaying trunks or in epiphytic soils, and that are eating using a very rich substrate as a feeding substrate. Once you have that kind of functional ordination of species, you can project on the factorial plan the different communities that you have sampled, the species lists and abundance. And here are the different habitats that we collected in the Nurags, and we can see that most of them were located near the intersection of the axis of this factorial plant, meaning that these communities had an even representation of each functional group. So this is a kind of guild proportionality pattern. But in a few cases, in the plateau and streambank forest and in the lowland forest, there was a dominance of specific functional groups. So in the plateau and stream forest, the large earthworms, this group A, was dominating the communities because these are deep soils where these species can find a good habitat. And in the lowland forest, these species that live in surface habitat were dominating because they were able to escape flooding during the rainy season. We also started, but these are really preliminary results, or maybe we can see these are perspectives, to go in phylogenetic diversity patterns. So we used DNA barcodes to calculate phylogenetic diversity in the different habitats of the Nurags. And we found a correlation between phylogenetic diversity and functional richness or quadratic entropy index, which are 2 very used indices of functional diversity. So this, in the future, we want to use this to infer from phylogenetic diversity patterns unfair assembly rules in communities. For example, in the Nurags, in the stream bank, plateau forest, and lowland forest, we had a high phylogenetic diversity and a trend to phylogenetic clustering, suggesting strong environmental filters in these ecosystems. And in the Inselberg, rocky savanna ecosystem and anthropogenic ecosystem, we had lower phylogenetic diversity and a trend to phylogenetic overdispersion, which should suggest the influence of competitive exclusion and limiting similarity in these communities. So just what are maybe the stronger results of our study? These very high level of local diversity, we were able to identify them thanks to DNA barcoding, high level of spatial turnover, beta diversity, and consistent functional structure among communities. And what are the perspectives? Well, in the nearby future, we will extend the sampling coverage of our study. We want to develop a comprehensive functional data trait database to go deeper into functional analysis of communities. And we want to investigate beta diversity pattern using not only taxonomic diversity, but also this functional and phylogenetic diversity. This will allow us going into historical biogeography and diversification processes. And we now have this DNA barcode library reference that we will be able to use in the future for environmental DNA studies. Thank you very much.
Thank you, Thibaud. We have time for a couple of questions. Yep, it's there.
Hi. I suppose earthworms don't move very far in their lives, and I'm wondering what the dispersion between conspecific individuals is in an ecosystem like that. How far apart are they, conspecifics?
It's difficult to make a general response to the question because in French Guiana, for example, we have a few species, invasive species. For example, we found in several sites, we found the African species. So these species seems to have a quite good capacity of dispersion, and other species will not disperse a lot. So I think it is very specific to the species, but there is not a lot of studies about that. In European species, it is several meters per year, maybe own dispersion by earthworm, but passive dispersion is usually a way for these earthworms to disperse in a far away.
Any other questions? Thank you very much.
Thank you.
Okay, before we break, I'd just like to reiterate a couple of points from this morning. If you haven't uploaded your presentation for this afternoon, please do it before you take lunch. Because we've ran a little over, our time for lunch is short. We'll be coming back here at 2 p.m. to start the parallel sessions. All parallel sessions will take place in this building. So this is where we're going to reconvene at 2. Also, because the parallel sessions will include presentations from students who are competing for prizes, those of you who have volunteered to judge, if you've not done so already, please go to the speaker ready room and get your assignments and scoring sheets so that we can score the presentations as they begin to take place this afternoon. We'll begin here tomorrow morning at 9. I hope we can begin very promptly to keep on time so that we have time for our coffee and lunch breaks. And I hope you enjoy your lunch. We'll see you back here at 2. Thank you.
Put to charge. I noticed one of them